in the middle, so from April to end of April this year. But with the pandemic, we had to shorten and suspend the run 1 month earlier. And we decided not to restart taking data, but to focus on the upgrades to come. So this is an example of the performance of a single detector. So the case of the Virgo detector that is in Italy. So science means that we are taking data that should be used for physics analysis, and that's in green, both here on the chart and on the pie. And you can see that we are able to take science data about 76% of the time. Locking means that we try to acquire the control of the detector that we lose from time to time, and then commissioning, calibration, maintenance. I'm sure you are all familiar with that. So that was for a single detector. If we move now to the network of 3 detectors, so the pie chart is showing you how often the different configurations are live, and you see that we managed to have almost 50% of triple coincidence, which is very good. That's what we have been trying to maximize in spite of the different time zones of the detector. And we also try to ensure that we have at least one detector always running. So we are completely blind on 3% of the time. And then you can see on the histograms below really the performances on a month-by-month basis at the top level of the 3 detectors individually, the 2 LIGO and Virgo, and at the bottom, the different 2 detector and 3 detector configurations. So I told you about the range before. So here you have strip charts showing how the range evolved during O3. So again, LIGO on Ford is in red, LIGO Livingston in blue, and Virgo in purple. And again, this is the same scale in megaparsec from 0 to 160. And the dashed lines that you may see well at the right show you what the performances were 3 years ago for the run O2. So you can see that all detectors have significantly improved in between O2 and O3. And so the vertical bar corresponds to this 1 month break that we had in between the 2 chunks of 6 months. And if you look below, you have the histograms of these BNS ranges. In gray, that's for the first part of the run, so O3A, and in color, the second one. And you can see that there are clear improvements also in O3B with respect to O3A, meaning that this 1 month shutdown break was very useful. So I will skip that one for the time. What I want to focus on rather is these public alerts, because we are analyzing jointly data in real time to try to detect potential sources, but also to localize them in the sky. And we send the information to the astronomer community using the NASA's GCN network. So here you have a sketch that is showing you the kind of latency that we expect. And basically you have to focus on the green bar. Within a few tens of minutes, we hope to be able to send alerts to the astronomers with some information about what the source could be and where it would be located in the sky. And you can find more information following that link. So on O3, so 11 months, 6 months, and then 5 months, we were able to generate 80 of these public alerts. Out of them, 24 were retracted by humans because we understood that the trigger was not due to a real gravitational wave signal, but 56 were not, and they were used by astronomers. So this is how those alerts are distributed over time. There is a very good accuracy between O3A and O3B. So finally, some first results for the O3 run. These are individual detections that we kind of say are exceptional. We had a signal on April 25th, 2019, which was likely the second binary neutron star detected, but that source was more distant and less well localized because it was only seen by 2 detectors out of 3, so no counterpart was found. The interesting thing is that the total mass is much larger than any known neutron star, so that may be the hint for a new population. Then we had JW190412, so detected on April 12 the same year. This is the first time we have a system with asymmetric in the sense that the masses are significantly different for the two components. And that has some interest also to test general relativity and predictions for gravitational wave emission. And finally, our most recent result, JW190814, so a signal detected on August 14 last year. This is the coalescence of a black hole with an object that has a mass of about 2.6 solar masses, meaning that it's either the heaviest neutron star in a binary system or the lighter black hole we've ever seen. And we don't really know what that thing is, but that's very interesting. And the mass ratio is much more asymmetric than JW1904. So there will be more results to come in the coming months. In particular, a new issue of our gravitational wave transient catalog. There are many searches ongoing. And I would like to stress that after some time, our data, our strain data become public. And so if you want to know more, you have this GWOS, Gravitational Wave Open Science Center website to check. So now O3 is over, and we're working on upgrades, and we should restart taking data in about 1.5 years. The exact schedule is still to be defined due to the pandemic. So I would like to close out by saying that you have this link where you can join this open LVM forum where you can have direct discussions with people from the library. Over.
Great. Thank you, Nicholas. Questions? I had a quick question, Nicholas, can you talk a bit more about O4, what is planned?
Okay, so for O4, the plan is to try to push by a significant fraction again the sensitivity, maybe by 30%, something like that. So there are hardware upgrades that are planned in order to reach that. And of course, all the planning has been put in jeopardy due to the pandemic. So there are workshops have been closed, firms have not been able to deliver material. So we are trying to assess where we are with respect to the original planning and see how and when we could restart jointly, because the idea is that whenever O4 starts, the 3 interferometers and also probably a fourth one with Kagra, the Japanese detector, should run together to maximize the potential of the network. So roughly in 1.5 years from now, whatever that exactly means, and normally with a sensitivity increase as significant as between O2 and O3.
Okay, thank you. I don't see any other questions, so let's move to the next talk. Thanks again, Nicholas. All right, so next we have Gabriella Cataldi talking about the Agar Prime upgrade of the Pierre Agar Observatory. Take it away, Gabriella.
Okay. Can you see my screen?
Yes, and we can hear you well.
Okay, thank you. It's a pleasure for me to present the Auger Prime upgrade of the Pierre Auger Observatory, and even if in virtual mode, I would like to thank the organizer for this opportunity. The observatory is located the Pierre Auger Observatory is located in Argentina. It is a giant observatory covering 3,000 kilometers square to compensate the very low flow at the highest energy of the cosmic ray of the highest energy. It essentially measures it has an indirect detection of cosmic ray through their atmospheric shower. And you see there are two main here, there are two main kind of detector, which are this surface array, which are intended to sample the shower when it arrives at the ground, the fluorescents that are spread all over the Pampa Amarilla in Argentina. And here the fluorescence detector overlooking the area. So those are 24 telescopes. And some more enhancement that allow in an infill area that allow to go better on the energy range of 10 to the 17, while here we are talking about more than 10 to the 17 electron volt as energy. The Auger observatory is based on an hybrid concept, which means that the surface detector as a 100% duty cycle is composed by these Cherenkov tanks that you can see over here in this picture. Essentially they have water Cherenkov tanks, while the FD, and as they can record everywhere, but they just see the projection at the ground, while the fluorescence detection is looking at the sky. So essentially the idea is that the atmosphere is as an enormous calorimeter, and we get the near calorimetric energy measurement. On the other side, since we are looking at fluorescence light emitted by the secondary, the duty cycle is very small, because we can record the light only on clear moonless night, so just close to the new moon. What is good is that having these two main detectors give a possibility to optimize the Auger hybrid data, because of course all these two detectors can acquire also SD and FD alone, but they can do cross calibration and avoid to use simulation when possible. So they can give various cross check. The Pierre Auger Observatory had an enormous amount of scientific result inside the high energy field. In particular, here you see the spectrum where there is this suppression above 5 times 10 to the 90, the presence of Henkel. And the other point is that has been very stressed by Auger was the mass composition study. So essentially that allow to spot the reason for the suppression of the spectrum, for example. The mass composition study, if you look at the observable that is more used for this, which is this Xmax, so the atmospheric depth at which the shower reaches maximum as the maximum size, you essentially see that here you have this change of composition. Here you see the plot of the hadronic model, the theoretical hadronic model for proton-initiated shower and iron-initiated shower. So it appears, okay, this is Xmax, this is the fluctuation of Xmax. It appears as you have a lighter composition above 2 eV. More talk about the Pierre Auger Observatory result will be given in this conference in the astroparticle physics session. So I invite you to follow if you are interested in the field. Another point always related to the hadronic model is that all the Auger data measuring the muon density fail to reproduce the latest simulation. So we always see a muon deficit in the simulated shower. Okay, those are data with Amiga at 10 to the 17.5, and those are inclined data at 10 to the 19. What was the science case for the upgrade? Essentially, when we go to look at the origin of the suppression at everything involve the mass composition, then we have a problem in sensitivity, because the main observable for us is Xmax essentially, but Xmax is better measured by FD, and we have an FD, a fluorescence detector that is only measuring on night where there is no moon, almost no moon. So in this region, that is the region here that is very interesting, for example, you have not enough data to understand what is the composition. So essentially, what was the idea of the upgrade? This is the same for muon, okay? If we cannot disentangle all over the area, the electromagnetic from the muonic component, then you cannot understand really what the muon part of your signal. So the science case for the upgrade is always related to the study of mass composition and the counting, the better understanding the muonic part. So extending the operation of the upgrade of the observatory beyond the 2025 was essentially not only to increase the statistic, but to improve the sensitivity on an event by event base. What is the concept? The concept is very simple. So we want to use a complementary of response of the detector to discriminate muonic and electromagnetic components. So for vertical shower, on top of the water Cherenkov detector, we place a further detector that, and from the difference in signal between the two detectors, we can disentangle the two components. For horizontal shower, of course, this is geometrically disfavored, so we use also a complementary of response, but in this case, we use water Cherenkov detector for muon and the radio emission for the electromagnetic part. And for this, there will be a dedicated talk in the following day in the same conference. Moreover, of course, there is an upgrade of the electronic and the addition of a small PMT in the water Cherenkov tank, which allow to extend the dynamic range in an area close to the core. Okay, so how is this detector done? Well, it's a very simple concept. Essentially, is a plane of extruded scintillator bar. You see here 160 centimeter long. There are wavelength shifting fiber going up and down, and there is only one photo detector placed in here. So this scintillator, which is 3.8 meters square, is read in a kind of integral way, just on the amount of light, then is calibrated for the number of detection. Okay, what the status of the upgrade? We have 12 upgraded stations, which was the engineering array, that are in the field since 2016, and they have a new electronic with the higher sampling, a large dynamic range, but I must say this station have not the final configuration of everything because they were used as engineering array, so for trying a different construction issue. Then we have the SSD pre-production array, which means 77 stations that are acquired since March 2019 with the old electronic, where we just unplug one of the PMT that was for the water Cherenkov tank to connect the PMT that is on the surface detector. Moreover, you see over here all this orange thing, we have deployed 752 SSD stations, not yet with the photomultiplier, but they are deployed in the field. The underground muon detector I didn't talk about, and the largest radio detector, as I told you before, there will be a dedicated talk in the next days in this conference. The
Gabriella,
production.
you have a minute to wrap up the talk.
Okay, the SSD production was a very long, was involving several institutions in Europe. And here is the status of the installation, where you see that we went quite smoothly, apart the last, the quarantine days. So this is the first data where you can see SSD and Water-Cherenkov detector, very different, the very different signal from SSD and Water-Cherenkov detector. And here you see how we can evidence the complementary response of the SSD and the Water-Cherenkov, disentangling the electromagnetic muonic shower component. So at smaller zenith angle and closer distances, the electromagnetic component has bigger contribution to the SSD signal. And while SSD signal become more dominant with increasing energy as the electromagnetic component grows faster than muons. To finish, the physics reach, one of the key elements is to understand if we can see a difference. For example, if we go to look at a maximum rigidity model, when we go to look at the spectrum, if we would be able to detect a 10% proton contribution that is not evident. So what we did is, with a standard scenario like this maximum rigidity model, where there are almost no proton, we feed 10% of proton, and we went to see how long we have to look for distinguish the scenarios of 10% more proton. And as you see here, in an operation time of 5 years, we will be able to evidence more than 5 sigma, given all the observable that we infer. I just leave the summary and outlook, and thanks a lot.
Thanks, Gabriella. Any questions for Gabriella? I don't see any hands raised. I had a very quick question, Gabriella. So the upgrades planned, what's the schedule for those to be finished, or?
Okay, in principle, it should have been finished by the end of 2020, at least the deployment of SSD. We had this stop related with COVID, of course. So all these, we are now starting again with a slightly different procedure because, okay, you see, it's not always easy to go in the Pampa. So it's, we tried with a slightly different procedure because now they are not allowed to go in 3 in a car. So in principle, they should go with 2 cars. So we believe we will go, we will end for the middle of 21. In the meantime, they are arriving the photomultiplier and the UV, the new electronic, so there will be the deployment together. What is good for the upgrade is that in principle, when you do the installation, you don't have to stop the acquisition. In principle, you just have 1 minute stop to plug and unplug the new photomultiplier. So it's quite fast, and you can still collect your statistic even if the detector is going with the upgrade.
All right. Thank you, Gabriella. I don't see any other questions, so let's move to the next talk. Next, we have Luca Moriscalchi. Sorry, Luca, if I didn't get that right, who's going to talk about the MUTI electromagnetic calorimeter.
Yes, thank you. I'm sharing the screens.
Right. By the way, we can see your Slack chat.
Okay. Can you see
now
the
we see the slides. Yes.
Okay. Well, good evening, everybody. I'm Luca Moriscalchi from the INFN of Pisa. And today I'm going to give you an update on the status of the MUTI electromagnetic calorimeter. MUTI is a charged lepton flavor violation experiment that wants to look at this channel, that is the coherent conversion of a muon into an electron in the presence of the field of a nucleus. Coherent conversion means that there are no neutrinos in the final state, and then the resulting electron will have a monochromatic energy that is slightly below the muon rest mass. For example, in the case of aluminum, that is the material we use as target, the energy will be exactly 104.96 MeV. As in the case of the other CLFV experiments, also for μ2e, any observation would be a sort of smoking gun signature for physics beyond the standard model. And it's important to remind that also in case of not observation, any experimental improvement in the measurement of the upper limits of this kind of branching ratios is of great help in constraining the parameter space of a lot of new physics models. So it's important. Our goal is to arrive at an upper limit of 8 times 10 to the minus 17 with a 90% of confidence level that represents an improvement of 4 order of magnitude with respect to the past best limit by the syndrome 2 collaboration. To reach this very high sensitivity, the first step is to generate about 10 to the 18 mnemonic atoms and to monitor their decays looking for our 105 MeV electron. The idea is to make collide an AGV proton beam with a tungsten target, producing mostly pions that decay very soon into muons, and to transport these muons through this system of magnetic fields and collimators until they reach this aluminum target, where they stop and form mnemonic atoms. The resulting conversion electron now should be identified by means of a detector that is composed of a straw tracker that is able to provide an excellent resolution on the momentum of about 160 kV/C, and a calorimeter, but housed inside this superconductive solenoid in a region where the magnetic field is uniform at 1 Tesla, so that the charged particle will drift first toward the tracker and after will hit the calorimeter. We are working at 100 MeV, so at this energy we cannot compete with the energy resolution of a tracker, but we can add some information that is useful to help in the experimental background reaction. For example, in μ2e, our main duty is to provide a particle identification to reject the 105 MeV/C momentum cosmic muons that pass our cosmic Revito system and then fake a conversion electron helix in the tracker. To do that in the correct way, we learn from the simulation that the most useful characteristic for a calorimeter is the time resolution that has to be better than 500 picoseconds, while the requirements on the energy resolution are more relaxed at the order of the 10% at the conversion electron energy. From a technical point of view, the project is not straightforward because we are working in a very hostile environment. We have a 10 to the minus 4 torr vacuum, and we are under a 1 Tesla magnetic field. And we are standing at the very high radiation fluxes that come from the interaction in the stopping target. We're speaking at something about 10 to the 12 1 MeV equivalent in silicon neutron per centimeter square, and a TID of 100 kilorad, considering 5 years of running and with a specificity factor applied. After a long R&D phase, in which we tried a lot of different solutions, we found a very good compromise between cost and performances in using undoped cesium iodide as crystal, coupled with some new generation UV extended silicon photomultipliers from Hamamatsu that has a very good PD at the 310 nanometers, where is peaked the CSI emission wavelength. At the end, our final design is composed of 2 discs separated by 70 centimeters. That is half of the pitch of the conversion electron helix in our magnetic field, just to maximize the geometrical acceptance. Each disc is composed of 674 crystals, and each crystal is read out by 2 different photosensors. Each of them is able to satisfy independently the request on the light collection, so to increase the redundancy of the system. The signals are sampled at 200 megahertz and are sent out through the cryostat using a system of 140 custom digitizer cards that are housed in crates all around the calorimeter discs. To validate this design, we built a large scale prototype of the calorimeter that we call Module 0, using 51 crystals. We tried to design the mechanics and the cooling system as similar as possible to the ones of a final disk, because so we had the opportunity to test all the assembling procedures and also to operate the detector under vacuum and at the operational temperature that is 0 degrees. We also exposed the Module 0 to an electron beam at the beam test facility in Frascati. Here you can see the resulting performances we had. We reached an energy resolution of about the 7.3% and a time resolution around 150 picoseconds at the conversion electron energy. As you can see, both of them widely satisfies the MU2E experimental requirements, and so we could start with the production phase, in which we received from the vendors about 300 photosensors and 100 crystals per month that we deeply tested through a very accurate quality assurance program. At the end, apart from some problem with the crystals from Saint-Gobain, because they weren't so accurate in the geometry, that is the reason because the qualification for the crystals isn't finished yet, because it took a lot of time. All the components we selected are of excellent quality. In fact, we rejected only the 4% of the crystals for some lack in the optical qualities, and only the 1.2% of the photosensors because they presented some disuniformities inside the sensor cells. All the components are now stocked at Fermilab in a dedicated clean room that we built to assemble the calorimeter discs. Just before the lockdown, we was finished to develop the procedure to glue the photosensors to their copper holder to prepare them for the integration with the front-end electronics. But during the quarantine, we had to stop. And since most of the people that is working on the assembling is Italian, it's not clear when we can restart due to the INFN and Fermilab politics on traveling. The status of the electronics is a little behind the one of the crystals and photosensors, because for both the front end and the digitizer, we had to develop more than one version of each board because we had some failure during the radiation hardness qualification tests, and we had to replace some components. For the front end, we just ultimated the version number 3 that mounts a new version of the ADC and the DAC. We tested it up to 100 kilorand, and now it worked very well. So the production started at the end of December. For what regard the digitizer, we tested the first version and we decided to change the optical transceiver, switching to the VTRX from CERN, the DC-DC converters, and also the FPGA, switching to the PolarFire 300 from Microsemi. Okay.
Luca? Oh, yeah. I was going to say, please wrap up.
Yes. To conclude, we can say that we successfully ended our prototyping phase and that we finally started the assembling of the first calorimeter disc, but that due to logistic problems in working at FNAL in these days, the assembling is freeze. What to say? I hope that the situation will stabilize soon so that we can restart to work physically all together and to have the possibility to complete this project. Thank you.
All right, thank you, Luca. Let's see if there's any questions. I don't see any hands raised.
I can't raise my hand because I'm a co-host, but I would have a question actually.
Please go ahead.
Sorry. So, of course, as everyone else, you're facing some issues due to COVID. So can you give an estimate of the delay that you could have due to these problems?
At minimum is 3 months, but we don't know when we will be able to restart to be in presence at Fermilab, because the politics from INFN are not clear, and for now we cannot move outside Italy, and all the assembling is based there, and so I can't estimate. I hope that in October things will be better and procedures will more clear.
Okay, thank you, Luca.
Yeah.
All right, thank you, Luca. We'll move to the next talk now. So next we have Katsuge Kotera talking about construction and performance of the cesium-iodide calorimeter in the Kodo experiment.
Yes, can you hear me?
Yes.
Okay, so I would like to share my screen. Okay, this one. Okay, can I start? Can you see
Yes,
my
please.
slides? Okay,
Yes.
so I'd like to talk about the construction and the performance of 4D CSI calorimeter for the Tailong to Kaiser Universe search of Koto experiment. The purpose of Koto experiment is to study the Tailong to Kaiser Universe mode. This mode is the direct CP violation, and the standard model prediction of branching fraction is 3 times 10 to minus 11, so very rare and sensitive to the beyond the standard model. And this shows our detector, as you can see, the decay region is hermetically developed, enveloped by the Vito detector. And this shows the electromagnetic calorimeter, CSI calorimeter. This CSI calorimeter is made of 2700 undoped CSI crystals, which has 27 radiation lengths. And the lateral segmentation is like this small one and like larger one. We have 25 by 25 square millimeter segmentation for the small crystals. And one of the difficulty of our experiment is neutron background. In this case, a neutron fakes 2 showers in the calorimeter, like this cartoon. And difference from the case of signal event is like this neutron reach to the deeper place of the calorimeter than the case of signal to gamma. So if we have the Z information in the calorimeter, we can separate the neutron background easily. And this table lists the background of the with 1.3 times 10 to minus 9 single event sensitivity. As you can see, this neutron background is dominant. And with those numbers, we estimated that at least we need to reduce the factor 10 of this neutron background for the standard model prediction. And so we had idea of the both side reader method. Then we installed this SIPM front surface of crystals like this. Then we have the time difference between MPPC front surface and rear surface PMT. We used MPPC as a SIPM. This merit is that we can take the UV light with this MPPC because we need to see the UV light in the CSI calorimeter. Okay, so to construction, we constructed on-site because to avoid disassembly of our detector like this. We use 4 MPPCs in a large crystal, and one MPPC in each small crystal. Like this, we glue MPPCs on 0.5 millimeter thick cords like this. And we made frames in front of CSI calorimeter and the jig to push MPPC toward the CSI front surface during the 16 hours cure time. Okay, I would like to go into the discussion on delta T performance. For that, we need to have neutron samples and gamma samples. For neutron samples, we had a special run. We installed aluminum target here, and then we required two cluster events. And so we had two delta T events, delta T maximum one and minimum one. For the gamma events, we used the K-long to 3-pi events, which has large branching fraction and loss contamination. For the gamma combination for pi0 events, we can solve that by that using a restriction of the invariant mass of gamma should be the pi0 mass, and the vertex of pi0 should be the 0 on the XY plane. So we had two delta T for each event, minimum and maximum. For gamma events, gamma events are pairs of gammas reconstructing pi0. And as you can see, delta T max has better selection ability for neutron events like this. So we plot the delta T max of the gamma events and the neutron events like this. If we required 90% of acceptance of gamma events, we see the remaining neutron events 2 times 10 to minus 2 of the original number of neutron. So very nice reduction of neutron. And we know that the K-long pi0 nu event has a larger energy cluster than the case of 3pi0. And the large energy cluster has the very more narrow distribution of delta T. So with the correction of energy dependence, we have more better neutron rejection power. Anyway, we had much beyond the first goal we got. And I would like to discuss about the remaining neutron background for Koto. We've already had other cut method like this. We call FPSD, which is see the difference of the pulse shape between gamma and the neutron. The other one is CSDDL, which sees the difference of the cluster shape of gamma and the neutron. And we tested the correlation between delta T cuts and FPSD or delta T cuts with CSDDL. With the FPSD, there is a small correlation between delta T and FPSD. However, still very nice the rejection power of a neutron. And the case of CSDDL, we confirmed that we have no correlation between them. And we estimated that remaining neutron events are less than less 0.5 in one standard model events. So very nice results from those. We can add another one more important parameter from the our new detector invariant, we call invariant time. So with this, we can say that we have 4D calorimetry. So this delta T invariant T is the average of MPPC time and the PMT time. Yes, and independent of the cluster depth. And if we need to measure the TOF of the primary particle and the secondary particle, this secondary particle was made by the primary particle. So certainly we have the time difference of them here. However, in the case we only use the PMT, the propagation time of the photon light cancel the difference. On the other hand, if we use the delta T, invariant delta T, we can see the net time difference of reaction. So reaction between 1 and 2. So we apply invariant. Yes.
Just to mention, can you wrap up your in 1 minute?
Okay. Time information and using because delta T invariant is proportional to the time of flight of the second particle, and delta T max is the proportional to the depth of second particle. So in the case of neutron events, we should have the correlation between the time delta T max and the delta T invariant. And as you can see, we can completely difference distribution of those, and we can succeed to reject the neutron events by these cuts at as you can see, less than 1 times 10 to minus 2 is the number of events remaining. Okay, so I summarized my talk. We developed the both-side readout method for Koto CSI calorimeter to reject the neutron events. We successfully installed 4,000 MPPCs. When 90% of signal remains, 99% of neutrons are rejected with both-side readout method with a 4D calorimeter. Estimated remaining neutron events are 0.5 with 1 standard model signal with delta T max and other 2 cuts. That's all from me. Thank you.
All right. Thank you, Katsushige. Any questions? So I see a question in the Mattermost from Luca. The question is, what is the integrated fluence of neutrons on the MPPC?
Integrated what?
Fluence of neutrons.
Fluence of neutron. Ah! Oh, in the case of with aluminum target, we have a lot of neutron. I forget the
right.
clear number.
Okay. Yeah, Luca is asking because MPPC are damaged by neutron fluence.
Very nice question. Because we've already measured. Actually, the MPPC has a large dark current by the fluent of the neutron, like this near beam is very large. However, we confirmed that if we have a lot of neutrons, for example, this case we tested it 10 to 9 of 1 MeV equivalent neutron per square centimeter has not so much change the timing resolution. Start time, we have 0.5 nanosecond time resolution. And with 16 times 10 to 9 neutron equivalent, the change the 1 to the 1 nanosecond. So, but this is not a problem. And our first measurement just here. So the MPPC is enough strong for in our case.
Okay, thank you, Katsushige. In the interest of time, we should move forward. I see one raised hand. Please ask the question on Mattermost, and speakers can answer there. Sorry about that. Thank you. Let's move to the next talk. We have Saskia Charity talking about the muon G-2 experiment.
Hi, everybody. Okay, I'll just, I need to wait to share my screen.
I needed to.
Yeah, can you stop sharing? Katsushige?
Okay. Okay.
Thanks. Okay. Okay. So thank you, everyone, for the opportunity to give this talk. It's a pleasure to talk to you today about the analysis of the magnetic field in the G-2 experiment. So I'll just start with a brief overview of the G-2 experiment and why we need to measure the magnetic field so precisely in order to measure G-2. So the experiment is aiming to measure this quantity A mu, where A mu is equal to G-2 over 2, and G is a dimensionless constant called the gyromagnetic ratio, which parameterizes the muon's magnetic moment. And what that means is that if you inject a beam of muons into a uniform magnetic field, the muon's spin will precess about the direction of that magnetic field because it has this magnetic moment. So A mu is the quantity that we're going to measure directly in this experiment, and that's also the number for which there's a theoretical prediction. And the current experimental measurement from the Brookhaven experiment sits at 3.7 sigma, different from the theory prediction. So that's the motivation for this experiment. So this is the G-2 magnet at Fermilab. The muons are injected into the storage ring magnet here. This is about 14 meters in diameter. And the charged muons will circulate around the magnet, which means that the muons will have a cyclotron frequency. But also as they're circulating, they'll precess around the magnetic field, which gives them a spin precession frequency. And the combination of these two, or the difference between them, tells us this omega A frequency from which we can directly extract A mu. And this is the frequency which you'll see in this wiggle plot, which if you're familiar with this experiment, you may have seen before, and which one of our colleagues is going to talk about in a separate session later in the week. But the other measurement that we really need to make precisely here is of the magnetic field. So how do we measure that? So in this equation for extracting A mu, the first thing we can do is just cancel out this term because of a convenient choice of running conditions. But we obviously need to measure B. So because we measure the magnetic field using proton NMR, we can actually make this, we can use this expression, and instead of measuring B directly, we can measure omega P, which is the precession frequency of free protons. So via a combination of other expressions, we can express A mu as the product of these ratios. And all of these other ratios here are known to very high precision. So the ratio that we want to measure in the G-2 experiment is omega A over omega P tilde. And that's what I'm going to talk about today. So what is omega P tilde? So omega P is actually the precession frequency of a proton shielded in a spherical H2O sample. So if we look at this cross section of the G-2 magnet, we see that we have a C-shaped magnet and the muons will go around the ring in between these pole pieces. And to make sure that we get a precise measurement of omega A, we need to make sure that this dipole field is very precisely vertical. So the field that we have, the dipole field, is strength 1.45 Tesla. But what happens, it's very difficult to keep a magnet completely uniform all the time. And from tiny changes in temperature, we can have tiny deviations to the dipole field from ppm changes in the magnet geometry. So we're actually trying to both mitigate and measure very small deviations in how parallel these pole pieces are. So there's two things that we can do. Firstly, we have a whole suite of measuring devices of NMR probes arranged in two different ways. So the main way is that we have a trolley which goes around the full storage ring every few days, and that measures a field map. So this is an azimuthal slice of the storage ring. This is the arrangement of the trolley probes inside the magnet. And this is the type of field map that you might get showing all the deviations from the dipole, which are very small, but we still need to measure. But obviously we can't have a big metal trolley in the way of the muons while we're taking muon data. So we actually stop the muon beam when we take a trolley run, and in between trolley runs, when the muons are there, we track changes in the field strength using fixed NMR probes, which are embedded above, just in the vacuum chambers above and below the muon storage region. So we keep track of all of the changes in the field continuously. These are read out every 1.5 seconds. But what we need to do then, because the field that we're interested in is the field that's actually experienced by the muons, so we need to interpolate between these every 3-day field maps using the fixed probes to understand what the field was at the time when the muons were present in the ring. And then the final stage of the analysis is to take the measured beam distribution, which is going to be talked about a lot more in the following talk, and we need to convolve that distribution with the field map distribution so that we can weight the field and actually get not just the field in the ring, but the field that the muons in the ring were most likely to experience. So how do we measure this field map? So the 2D field map, if you consider again this azimuthal slice, and what we're actually interested in is we can average that slice all around the ring to understand the average field experienced by the muons. So we can approximate this 2D field map as a multipole expansion. So to explain some of the terms in this equation, B0 is the dipole term, which is uniform everywhere. And this is what we're trying to keep constant at 1.45 Tesla. And I should have mentioned on the previous slide that as well as measuring this, we actually have feedback systems. So we can dynamically change the magnet current to try and any larger deviations, we control that by making sure that what we're actually setting the magnet strength to is uniform all the time. But if we expand this, we obviously have higher order terms, and these can be described as sort of shapes that you see in the field map. So these cosine terms we call normal terms, which are symmetric about the vertical axis. And the sort of most important ones that you're going to hear about today are this normal quadrupole, which manifests as a radial gradient across the radius there, and this normal sextupole term, which has a shape like this. And the sine terms are not symmetric about y equals 0, and we call these skew terms. So that's what they look like. So just bear sort of the higher order ones of these in mind, or the leading order ones. Okay, so how do we extract these moments from the NMR probes that we have in the ring? So as I mentioned, we have a trolley that goes around. And because we've got the probes actually in the place where we're trying to measure the field there, we can form a 2-dimensional fit to these probes to extract the multipoles, to extract these coefficients from a 2-dimensional fit. And this is what we call a multipole expansion. But with the fixed probes that sit above and below, so this is a top-down diagram of the ring showing the location of all the fixed probes. So in some places we have 3 above and below, and this is what we call a 6-probe station. In other places we have 2 above and below, and this is what we call a 4-probe station. And we can make a geometrical combination of these probes to work out what the changes, what the shape of the field between them would be. So for a dipole, you would just average all the probes. if you wanted to know if you can also subtract the lower ones from the upper ones to see if you've got a shape with a gradient vertically. You could subtract the inner from the outer to see if you have a radial gradient. And we make various mathematical combinations of these probes in the different stations to predict the multipoles using those. So something else that we have to do is take account of multipole mixing. So we can't just measure each one. We have to take into account the fact that some terms are going to bleed into one another. So as I said, if these blue dots are the fixed probes, the dipole is going to be an average of all the probes. But if we had a normal sextupole shape, which this plot is, if the normal sextupole changed or increased, all of these probes are going to see the same increase. They're going to move in the same direction. So we have to make a correction to the dipole term to account for the fact that there was a change in the normal sextupole. And the normal, sometimes other moments can bleed in as well, but this is one stage of the analysis, is we have to take account of this multipole mixing. So the next important thing to do before we can start tracking the field when the muons were there is to synchronize the trolley measurements and the fixed probes. So as the trolley drives underneath a fixed probe station, the trolley actually has its own magnetic footprint, which is seen by the NMR probes embedded in the vacuum chambers. So that kind of looks like this, and we can actually parameterize this with a double Gaussian, make a fit and work out the exact time that the trolley was underneath those probes, and that's how we assign the synchronization time. And once we've synchronized the trolley measurements, we can take our fixed probe measurements, set them equal to the trolley measurement at that time, and then we just track the changes using the fixed probes over time. So this is a plot from one of the run 1 sets. We have 11 sets like this in the run 1 data set in the full thing. So we track these changes over time. And this is what we call calibrating the fixed probes of the trolley measurements. But as you see, the calibration can drift over time. So you tie this together at the start, but you end up with a difference here. So we take the second trolley measurement and we recalibrate all the data for the fact that we know the trolley measurement here. So we can recalibrate all of those. And this difference we refer to as an interpolation discontinuity. And there are 72 fixed probe stations around the ring, and each station is going to have a slightly different interpolation discontinuity depending on the changes in the magnet and temperature and things like that around the ring. And this will be different for different data sets. So for each data set, we can take the interpolation discontinuity of each station and use that to parameterize the interpolation uncertainty for that data set. So how we do that is by considering, if we consider the changes in the magnet that we're tracking as a random walk variable, but we know that it's bounded at both ends because we take these two measurements, we can actually consider this as a Brownian bridge process. And all that means is that if you have your random walk, you can subtract out a linear term, and that shows that you're bounded at both ends. And this helps you reduce your uncertainty because of the statistical likeliness of the direction of your random walk. So if you knew that you're bounded here, it's statistically unlikely that your process actually followed this path, because then it would have to snap back and come back to match this value. So it's the most statistically likely one is that it just drifted between them and came back to match it here. So this plot here shows the uncertainty versus time for a trolley pair of different lengths. So I said that they're approximately every 3 days, but some might be a few hours longer, some might be a few hours shorter. So if you've got a shorter time between trolley runs, you'll have a lower maximum uncertainty than you would if you had a longer time between trolley runs. But if you didn't bound it at all, then your uncertainty will just continue to grow because you couldn't bookend it at the other end. So as I say, we use the distribution of the 72 interpolation discontinuities. We make a histogram and we use the mean and the RMS of that histogram as input to a Monte Carlo based simulation to understand the random walk for each data set. And this gives us an uncertainty specific to that data set for how well we know the field in the time in between the trolley runs.
Lesky, yeah, you're out of time, so please wrap up.
This is very, very nearly the last slide. Okay, thank you. So this is just a really preliminary uncertainty table. So the only ones I've talked about here today are the interpolation uncertainties, but I just wanted to highlight that we're beneath the target of 70 parts per billion, even in the longest trolley pair for run 1. So this is just an uncertainty table for one of our trolley pairs in the run 1 data set. And I know I'm out of time, but just had one more slide about the muon weighting. So Sudeshna next is going to talk about the beam distribution, and the analysis procedure is also in place to take the time-dependent beam distribution and convolve that with the magnetic field as a function of time between the trolley runs. So that's everything I wanted to say. Sorry, I went over a bit. Thank you.
That's all right. Very nice talk. Thank you. Maybe one quick question. I don't see, oh, I see one hand raised. Let's see. Can you unmute and ask the question quickly? Does the host need to unmute the person who raised the hand?
Based.
Oh, sorry, I don't see the person connected anymore. I suggest to ask the question over the Mattermost channel.
I'm sorry, it was me from the personal account, and so it will be easier if I ask here.
Yeah, go ahead very quickly.
Yeah, my question is about, so you also then have to calibrate the absolute position kind of the magnetic field, right? Because also the probes can move kind of. Is that important?
So the motion of the probes and the trolley run are obviously moving, and that's a large part of the analysis to get the trolley field map, is to really understand the effect of how well the trolley probes can read the field while they're in motion, and that's quite well understood, but there's an uncertainty associated with it. We don't consider the motion of the probes in the vacuum chamber. I think that would be a small effect. But again, I guess if they're moving because of changes in the magnet gap associated with temperature, that would manifest in changes in the field, so we can analyze it that way. But we don't have to explicitly, they were mapped and we do understand the positions. And the azimuthal position, although we might not be that sure about those, we always can calibrate using the trolley footprint to make sure that the trolley and the fixed probes are completely aligned. So we use that measurement to make sure we're in the right position when we calibrate those measurements.
I see, thank you.
All right, thank you, Saskia.
Thanks.
Let's move to the next talk by Sudeshna Ganguly, talking about the G-2 beam and systematic effects for run one. Sudeshna, please go ahead.
Hi, yeah, sure. Can you see my slides?
Yes.
Okay. So, hello everyone. I'll give a brief overview of the muon G-2 beam and spin dynamics for our run one. So this is what I will do. Saskia has given already a very, very nice overview, so I will be very brief on that. Then I will talk a little bit about the muon injection, storage, and some of the detectors that provide us with the useful beam dynamics information. And then I will talk about some of the most important beam dynamics related systematic effects. So we start by injecting a polarized beam of muons into our storage ring. Upon injection, the muon spin and the momentum, they're aligned, hence a highly polarized beam of muons. So the muons circulate around the ring with this frequency omega c, the cyclotron frequency, and the spin processes around B with this frequency omega s, and the difference is omega a. And that's related to A mu directly. So omega A and omega P, what we measure experimentally. And our goal is to achieve a fourfold improvement over BNL measurement. So let's talk about beam injection and storage. So we have the inflector magnet right here, which provides the beam a path to enter into the storage ring. So this is basically canceling the magnetic field in the magnetic gap, this inflector magnet, and bringing the muon beam into the storage ring without it being deflected. So when the beam enters, it's 77 millimeter offset from the center of the storage ring. So to align the incident orbit onto the ideal orbit, the design orbit, we need to kick the beam some more, and we have the kicker magnet for that. And the storage ring itself provides a radial confinement to the beam. But we need the vertical focusing as well, or the beam will spiral out. So we have 4 different discrete quadrupole system, which electrostatic quadrupole system, which provides the vertical focusing. So the effect of the E field cancels out to the leading order when we run our experiment at this particular momentum, which we call the magic momentum, 3.09 JeV. So this cancels to the leading order, given that we run at this momentum. So when the muons entered the ring, all muons have spin pointing the same way because fully polarized beam. So at some random time, they will then spontaneously decay to decay positrons, and the emitted positrons will have lower momentum than the parent muons. So they're gonna curl inward towards the center of the ring. And we have 24 calorimeters all around the ring. So this is a calorimeter station. Each calorimeter has 54 lead fluoride crystals with very fast CPUMs. So these detectors will provide us, they provide us with the information about the decay positron arrival time and energy. Then we have 2 straw tracker stations, one at 180-degree location. So this is 0 degree, this is 180, and one at 270-degree location. And they provide decay positron trajectory reconstruction at these 2 locations. So the decay positron trajectory then can give us the information about decay muon distribution, as you can see here. So now let's move on and talk about some of the most important beam dynamics related systematic effects. We need to have a very detailed understanding of the muon beam behavior through production, transport, injection, and within the storage ring. That is important to extract the precession frequency omega A because there are some important beam dynamics related systematics that will pull the fitted value of omega A. So we want to have large positron statistics because we want to maximize our storage efficiency. And detector acceptance and along with the coherent beam motion, that should also be included in the decay positron fit function. So we need a very realistic beam dynamics model that goes around the storage ring and is constrained by the tracker data. So here you see the decay positron time distribution, the famous wiggle, fitted with a simple typical 5-parameter fit function. And this is showing the FFT of the fit residual. You can see for the red lines, which is just with 5-parameter fit. So this needs to be corrected for effects such as lost muons, which is showing here, the early rays. You can see some of the beam dynamics frequencies, coherent Betatron oscillation, vertical waste, etc. So once you incorporate these beam dynamics effects in the fit function, as done here in the black line, which is the full fit function, then you can see these peaks disappear. So the 3 beam dynamics related systematic effects I will be discussing are phase correction, electric field correction, and muon losses. So for muons on ideal orbit in a horizontal plane under uniform magnetic field, so that's the ideal condition, omega A can be approximated by this equation. And our experiment is sensitive to components of the spin in the direction of the momentum to leading order. So in the idealized version of the omega A, we ignore 2 important beam dynamics effects. So one is the torque exerted by the electric field, and other is the change in the rest frame magnetic field resulting from the vertical pitching motion of the muons. So these 2 corrections must be applied to omega A. So our experiment is designed around injection and storage of muons centered on the magic momentum, which is a 3.09 JeV momentum. So the magnitude of this term is maximum when beta or the momentum and the B are perpendicular. So for any vertical motion, the magnitude of this cross product will decrease. So basically pitch term is decreased by the sign of the angle between the momentum and the field. So now let's talk about the muon losses. We do have the unavoidable phase-space injection mismatch to the storage ring. So only a few % of the muons can be stored. So a muon can be scattered out of the storage region if it strikes one of the collimators, which define our storage aperture. So generally, most muons which are on the outer periphery of the phase space that cannot be stored are removed within the first few turns by quadrupole scraping. We move the beam, scrape it against the collimator and get rid of those muons which cannot be stored. However, a very small fraction can survive for many, many hundreds of turns, and they can sneak into our measurement period. So these muons which are lost during our measurement period can affect the fitted value of omega A if they have a preferential average spin phase different than the average spin phase of the stored mu1. So that will give rise to another systematic effect. So let's talk about the pitch correction in more detail. So particles injected into the storage ring will have a vertical component of momentum, which is parallel to the magnetic field vector due to vertical beam motion. So this will slightly reduce the magnetic field seen by the muons in the rest frame. So basically then pitch correction depends on vertical Betatron beam motion, and vertical motion is modulated by the quadrupole electric field. So pitch is different for different quadrupole set points. So the term is shown here, which is dependent on the vertical distribution of the decay positrons. And we use the straw tracker to measure that. So you can see the vertical position here looks closely centered in the storage region, which has a width of 90 millimeter. So we have used data-driven analysis. Analytic approximation was done based on this measured distribution, but we also have spin calculation. We can have that to verify these data-based methods, and the spin calculation will become more and more important for higher precision corrections for future analysis of the later runs. Let's talk about the electric field correction then. The electric field correction accounts for contribution from non-magic momentum muons. So our experiment ideally operates near the magic momentum to minimize the electric field contribution. So the main magnet field is chosen so that the closed orbit of the magic momentum muon corresponds to the design trajectory. But we have a momentum spread, so not all muons have magic momentum. So that gives rise to this correction. So for the non-magic momentum muons, this extra term depends on the momentum of the particle and the electric field strength. The stronger quadrupole field defocuses beam, and then it will push off momentum muons farther from the storage ring center. So the spread in the momentum or the equilibrium radius also depends on the strength of the quadrupole electrostatic field. So the correction, the electric field correction is proportional to the equilibrium radius of the beam. And here you can see the equilibrium radius distribution from 4 different run 1 data sets. This is a preliminary plot again. And this was determined by Fourier method, a technique based on Fourier transformation, which will give frequency spectrum that can then be correlated with radius and momentum. So now we have a class of systematic effects where spin correlation can combine with the early to late effect. So spin correlation means when d phi over dp is not equal 0. And then early to late effect is when momentum dp over dt is not equal 0. So when you combine these two together, you have d phi over dt, and which makes phi as a function of time. So this is a linear frequency term. So phi being a function of term then will lead to a pool on omega A fit value. And muon loss is an example of such kind of systematic class of systematic effects.
So 1 more minute to wrap up.
Okay, sure, I'm almost done. Yeah, so assume that we have 2 different ensembles, lost muon population and stored muon population, and we start with the same number of muons, and suppose they have different spins, the 2 different ensembles. So each population has a different depletion rate. So dp dt not equals 0. And there is a possible connection between the momentum and the phase of the muons entering the ring. Muon losses during storage d phi over dp. So when you combine these two, that makes, this is an early to late effect and spin effect combined together. So we detect the lost muons by looking at the consecutive calorimeters. They punch through the calorimeters and deposit MIP-like energy. And you can also look at the time of flight. So this is a typical muon loss triple spectrum obtained from 3 different calorimeters, 3 consecutive calorimeters. And this correction term enters into a fit function, which accounts for the losses. So basically this number gives you the absolute loss rate. So then you combine that with these 2 quantities. So these were measured using some special systematic run where it shows the d phi over dp And dp over dt were obtained by using probability of losing a muon as a function of momentum, and by performing fits, which were then constrained by the equilibrium radius distribution. So this is equilibrium radius distribution and last muon measurements. And then we got the equilibrium radius, then convert that to dp over p, and combining these two will give you the size of the effect coming from the losses. So I'm on my summary slide now. So to summarize that, we have these well-known corrections from the pitch and the electric field contribution, which have been refined and performed detailed analysis uncertainty. So we use a tracker to get the vertical muon distribution. For electric field, we get the radial distribution from the time evolution of the incoming muon bunch. And the lost muons, they lead to a small spin effect in the run one error table. So sorry. So the size of the error from the last muons are well within the budgeted error in our TDR. So that's it. Thank you.
All right. Thank you, Sudeshna. Questions? Maybe we have time for one quick question. Okay. I don't see any hands. Sudeshna, I'm sure you mentioned this and I missed it. You presented a class of systematics, you know, of which one is dominant and how well you do to.
So yeah, so hold on. I have a, yeah, so I was talking about this one where the budgeted error is about 20 ppb and we're well within that from run one, and E-field and pitch correction. So the size of E-field correction is about 480 ppb with the error of about 50 ppb from run one, and pitch is about 170 ppb, which is the value, and then the uncertainty is about 20 ppb. So the pitch was different for different quad values in run one. And E-field correction varied with kick, different kicks during run one.
Okay, thank you. All right, let's move to the next talk then. The last talk of this session, we have Paolo Zuccan talking about pixel detector for tracking in space.
Okay, hello everybody, can you hear me?
Yes.
Okay. Can you see my share?
We see a black screen. I think if you share your desktop rather than a particular screen, that may fix it.
Yes, sorry. Is that working?
Perfect. Yeah.
Okay. Hello, everybody. I'm Paolo Zuccan from Toronto University and INFN. And I will talk about the use of the Alpide pixel detector developed for Alice for tracking in space. So many of you probably know, the Alice collaboration developed a new pixel sensor for the inner tracker upgrade. It's implemented using CMOS technology, and each sensor is 1.5 centimeter per 3 centimeter, and it contains 512 for 1024 pixels. It exists in two versions. One 100 micron, one 50 micron of thickness. And substantially, it's a deep PWL, which allow the PMOS electronics to be hosted on the surface of the sensor, while allowing the rest of the silicon to work as a particle detector, charging where the pixel collect the charge by diffusion. Our idea is to use this detector as the tracking system of this experiment that should fly on board of the Chinese satellite XS. The whole detector is based of a silicon tracker, followed by a plastic scintillator calorimeter, which ends up on a LISO calorimeter. The idea is to measure the fluxes of protons and electrons trapped in the Earth magnetosphere in the energy ranges of from 5 to 100 MeV for electrons, from 30 to 300 MeV for protons. The point is that this Alpide has been designed for ALICE and LAC detectors, which use mostly MIP, and in particular, so we want to use it on a different domain and with slightly different energies. Sorry, this is the layout of our tracker. The idea is that we host the 10 chips of Alpide in 2 rows, and we mounted these chips on a carbon fiber and 2 end block in aluminum. Then we pack 3 of these objects that we call stave in what we call a turret. So where particles cross through, leave 3 points, and we can reconstruct a track. And then we combine 5 turrets, and we obtain our full 3 layers silicon detector that is roughly 15 centimeter by 15 centimeter of active area. At the moment, the design of the readout tracks for the detectors, what we call the FPC, has been tested and produced, and also the mechanical has been tested and produced. We are going over the fall of a production, a full turret with this tracker splitting electronics, and then we go for a production of the full tracker. Sorry. So what are the challenges for use a detector in space? First, we need a light support that should provide no multiple scattering. At the same time, this support must withstand the launch acceleration and strong vibrations. And these are competing requirements. The other point is that we have to dissipate the heat, but we don't have air. So we have to use this or dissipate this heat all through the carbon fiber that is also the support. We cannot use any material. We use material that do not outgas much in vacuum and well behave in vacuum. And most of all, we have to operate these detectors with a very limited power budget. So we first then developed an extensive study of the support material that must be stiff, must be must transmit correctly the heat, until we found a system where the heat is well dissipated through the end block of our mechanical support that we call stave. The next big issue is the power budget. Here you see the Alpide deployment on ALICE. You see they have what they call inner barrel mode, where each sensor works as standalone, and what they called outer barrel mode, where there is one chip working as a master and 7 chips working as slave. In our configuration, you see there's the possibility to have the slave chip to consume much less. So for first choice has been to use this master slave, where we have 2 masters and 8 slave for each stave, each tracker module. Then we had to switch off the data transmission unit. This is, you see this green part that accounts for large power. that so we do not use the standard transmission unit from Alice, which is high speed, but we had to develop our own data transmission using the backup control line in the Alpine power. But this allows us to save still a lot of power. You see the further step we had to implement is clock gating. If we switch off the clock, you see we move from 17 milliwatt for square centimeter to 7 milliwatt for a square centimeter. So we use a strategy of clock gating where the default clock is off. When a trigger arrives, clock is turned on. We wait for signal desensitization. We read our data and we switch off the clock. We can do this because our acquisition rates are relatively low. And as we see, when using this gating technique as function of the trigger frequency, we reach a power consumption over the whole tracker, you see, of about 7 watt if we enable just one turret for trigger, or 8.5 watts if we enable 3 turrets every trigger. We can do this because our trigger is segmented with the same segmentation as the turrets, and so we can activate the turrets basing on the trigger information. The point is that nothing of what was developed for Alice was possible to use directly in space. So we had to develop a new low power DAQ for the detector. And this DAQ, again, as must be low power, must control Alpide and collect the data through the slow D control serial line, and must be satisfy criteria very important for space, that is modularity and redundancy. The board is 2-part hot and cold. It's implemented with Xilinx Arctic's low power, and where we wrote the HDL for implementing the AQ and control, and we activated a soft processor where we wrote the calibration and service procedures that are slightly more complex. But we keep the possibility to switch the processor off most of the time during normal operation. So during the DAQ, the processor is off. So finally, we develop the firmware modularly, where we developed a module that is capable to control and read out the single stave. And so we control the full tracker by multiplying these control modules that could eventually work in parallel. So we have these 15 state machines that control each stave. Then we have an event builder that collects the data from the staves and do some compression before offering the data on out buffer for the main CPU when the main CPU will ask that for them. This part has been fully implemented and tested in several equipment. This is an idea of the calibration procedure we can perform, what's called threshold scan, where we inject charges, growing charges into each pixel, and we count how many pixel responds on to that level of charge injection. This allows us to find the threshold of that chip and then tune the parameter to tune the thresholds as required.
Paolo, 1 more minute to wrap up.
Yes, and mostly picture from here. Very recently, we were able to really build and assemble a full turret composed of 3 staves. This has been assembled at INFN Turin and has been tested with our the ACU system at Trento. All this has been brought to the CERMS laboratory for space qualification in Terni, where this EM module version of our tracker turret has been vibrated along the 3 axes. Here I show the picture of 2 of them. We also performed some data acquisition. This is noise and muons. You see horizontal muons leaving tracks. And also we tested the sensor in thermovacuum chambers. And you can see that when temperature is high, we have a slightly larger noise and muons track. At lower temperature, mostly muon tracks. So my conclusion, the endeavor or porting the Alpine silicon tracker in space is proceeding. Design has been finalized. Mechanics support has been designed. Prototype has been produced. Low power DAQ has been produced and tested. And a full tracker turret successfully passed the space qualification test as the vibration test. And all points to a fruitful implementation of mapped pixel technology in space very soon. Thank you.
All right, thanks, Paolo. Any questions? I see Gabriela has a question. Go ahead.
Yes, I would like to know if there are, what are the trigger rate, because I assume you expect a polar region orbit, or I misunderstood something. So
no,
what
you're
are
right.
the trigger rate?
You're right. We will fly on a very polar orbit, and we expect the trigger rates up to 1 kilohertz substantially. Our dimensions are not that big.
Okay, thank you.
You're welcome.
Great.
Remember, it's 15 by 15 centimeter, the tracker, and then you have to account for the geometrical factor of the detector. All
right, thanks, Paula. That's the last talk of the session. Thanks to everybody, great set of talks. So we're running 3 minutes late, but we'll take a 5-minute break so people can stretch arms and come back. So we're on different time zones, but let's come back here in 5 minutes from now.
Thank you, everybody.
Thank you.
While we're on the break, for speakers of the next session, feel free to use this time to check your screen share and such. If you somehow already tested before the beginning of the first session.
Hello. Maybe I would like to ask ZTA if you can again stop sharing this
Sure.
meeting. Yeah.
Yes.
And yeah, if somebody needs test sharing, please, you can, of course. Yeah, we can see.
All right, that's about 5 minutes according to my clock, at least. So this session is about neutrino detectors, and we'll hear from several experiments: microboon, protojoon, solid. So let's get started with the first talk. And again, the format is the same as before. Wait for the speaker to finish the talk, and then at the end, you can raise your hand and wait for me to call you to ask questions. There is also Mattermost channel, more like a chat platform where you can ask questions there as well. Let's see. Relitza, I see you're connected. Would you like to go ahead and share your screen? Relitza is going to talk about the microboon experiment.
Hi, and thank you. So yeah, I'd like to start with a couple of words on the short baseline neutrino or SBM program at Fermilab. The program was started after the miniboon experiment observed an excess of events over Monte Carlo in the low neutrino energy, which was hinting at some beyond standard model physics. But other than investigating this excess, the program also aims to do very precise measurements of neutrino cross sections aimed towards future experiments like Dune. And the program consists of 3 experiments and 3 detectors. All of these are liquid argon time projection chamber type detectors. Microboon was the first one. It was so sitting at about 500 meters from the beam target. It started operating in 2015. The second one to start operation was now called the fire detector, basically the Icarus detector, which is currently in commissioning, and then SBND is still under construction. So microboon, as I said, was the first liquid argon TPC detector from the SBM program to start operations. And I should perhaps first say that the choice of technology for the program was driven by first the excellent spatial resolution of large TPCs and also the good colorimetry. And both of these are important for both electron to gamma disambiguation, but also for being able to identify complicated final state topologies and to study them separately. So microboon, for the almost 5 years of operation, has done a lot of pioneering work, both in data processing, noise filtering, some kind of low level development, but also in calibration, event reconstruction, physics, also detector physics, etc. Just to give you, a quick reminder of how the technology works. So when you have a neutrino or any kind of interaction inside a detector, which produces charged particles, these charged particles will ionize the argon inside your detector, and then the ionization electrons will drift in electric field towards the anode plane, and of course the positive ions will drift towards the cathode. In the case of microburn, the electric field is about, in practice, about 273 volts per centimeter, 500 at design value. And the 273 results in about 2.3 milliseconds, a pretty long readout window. So when the drift electrons reach the anode plane, they pass by two induction planes, where they would induce signals and are finally collected on the third, the collection plane. And the 3 planes in total in microburn have more than 8,000 channels. And what the signals look like is shown. The example here is basically 2D projections on the 3 planes of the 3D trajectories. But in addition to that, in addition to the TPC signals itself, the charged particles with side argon produce excimers, and these excimers at de-excitation produce isotropic UV scintillation light, which of course reaches the ends of the detector almost simultaneously and is observed by a photon detection system. So as I said, during its almost 5 years operation, microburn has done a lot of pioneering work. I've listed here a lot of our publications on technical stuff like noise removal, shown on the left-hand side, signal deconvolution and simulation of the signal of the wire signal response. And then of course, also charge and energy calibration on the right-hand side. And I'm not going to go into detail about all of these, of course, because of time constraints, but you can check the publications. And as I already mentioned, we have also done a lot of development into software. The experiment has several independent frameworks for event reconstruction that are listed here. And these are complementary in the sense that they use different techniques, but they can be combined or not for neutrino event reconstruction. And please go ahead and check the publications here if you're more interested. The 2 things that I will talk in more detail about are measured here. Basically, both topics are detector physics. One of them is measuring space charge effects, and another is talking about PMT gain calibration. So what is space charge? Basically, we sit at the surface, so we see a very large cosmic ray flux. And the fact that the electric field is lower than design value basically means that you have a lot of slow-moving argon ions that form in the detector and take longer time to reach the cathode, of course, than it takes for the drift electrons to string the anode. So we end up with this kind of localized pockets of positive charge. And what this means is that you get local distortions of the electric field, and also the paths of the drift electrons get distorted, which in reality results in the tracks and showers that you reconstruct looking bent. And I'm showing an example here in the bottom right. This plot shows the endpoints are the start or end of reconstructed data muons. And you can see, so the dashed square represents the detector boundaries. You can see that as you go closer to the cathode, which would be high X in this plot here, at the right-hand side, your tracks start to bend inwards. And in order to, study these effects and calibrate them out from the data in Monte Carlo, microburn has developed 2 methods. One of them uses data from our laser UV system, and the other one uses cosmic rays. And I should point out that both of these are complementary, and we actually use a combination of both methods in our data analysis. I'm going to talk in a little bit more detail about the calibration method with the laser UV system, which was just published. So the system itself consists of 2 laser units sitting upstream and downstream of the detector, and both of these inject 266 nanometer UV laser inside the TPC. And through a system of mirrors, you can see we have a very good coverage of the full detector as shown in the laser path schematic on the bottom. And there are 2 main things that we measure with this method. The first one is basically the deviations in reconstructed position at any point of the detector. So you do a scan to cover the full detector volume. And what you measure is the distance between the reconstructed track, shown here in red, and the actual laser trajectory that you would expect, which is shown here in blue. In the bottom, I'm showing an example for this data measurement, because again, the paper is on data. This is for just one slice in the detector, is the central slice at Z equals 518 centimeters. And if you look at the maps, for instance, for the deviation in the reconstructed X coordinate, which is drift direction, or Y, which is vertical, you can see what you kind of expect. You see more larger deviations as you go close to the cathode plane, and much less deviation when you go to to a smaller x, and it's more or less uniform over z. The second measurement that we do is a measurement of the localized distortions of the electric field. And actually how you do it is you measure the local drift velocity, as shown in the schematic here, and then you extrapolate to, not extrapolate, but you convert that into E field using the function shown here. And again, at the bottom, this example for the center slice, you can see more or less the same. The effects get larger as you go towards the cathode, where you get the larger concentration of positive ions, of course. So moving on to the second topic that I want to talk about, this is about PMT data. As I said, in liquid argon TPC, you get this UV scintillation, and this is read out by a photo detection system. In case of microburn, the photo detection system consists of 32 8-inch PMTs that sit behind TPP coated acrylic plates. They are fixed on a frame that is behind the readout wire planes, as shown in the picture in the bottom left. And of course, the role of the TPB is to shift the scintillation, which is UV, to visible where the PMTs can actually record it. And now what do you use the light for? Well, you can use it for many things, but in our analysis currently, probably the biggest thing is cosmic ray reduction. Of course, because of the low neutrino cross section, even beam spew events are generally empty. You have no neutrino interaction inside the detector, just cosmic rays. And one way to reduce this kind of empty spew events is to require large activity coincident with the beam, large activity in the PMT coincident in the beam, because cosmic events in general will generate less light. Now, this method of triggering on PMT information helps us drop the trigger rate by a factor of 50. And then there's a second method that we use called flash matching, in which case you're basically trying to match a reconstructed TPC object, so a shower or a track, to the light that is coincident with the beam spew. If you see difference, this discrepancy, the reconstructed TPC object is likely not related to the beam activity and is an out of time cosmic. But to be able to do this kind of analysis over the full 5-year data taking, of course, we need to understand the light response of the detector very well, and for that response it needs to be flat in time. And in fact, there are things that can cause your response to fluctuate. For instance, PMT gain. It can fluctuate, of course, with voltage. It can fluctuate with temperature. It can fluctuate even with the amount of light that you're seeing at any given time. As well as light yield itself, the liquid argon, that can change with, for example, the amount of impurities that you have in the liquid argon at a certain point in time. So it's important that we calibrate these effects out so that we get a stable and flat response for the full data taking. I'm just gonna talk in a little bit more detail about our PMT gain calibration. This plot here shows evolution of PMT gains for just a handful of the 32 PMTs shown from the beginning of data taking to some point last year. And you can see that early on in data taking, a handful of the PMTs actually show pretty large deviations, up to 30% from the mean value. And to correct for that, after this was realized, some new procedures were implemented where we actually started monitoring and implementing calibrations regularly. And of course, I should point out it's important that we do this kind of measurement and we do apply the correction to bring this data back to the nominal so that the data MC agreement is good over the full data taking period. And I should also point out that this kind of long-term measurements are important because they just give you an idea of the long-term development of gain in liquid argon TPC PMTs, which can be useful for future experiments that use PMTs. But it also helps, by flattening the response of the PMTs. It lets you then independently measure other sources of light response instability, such as impurities, etc., which is what we're doing in microburn.
Let's say 1 more minute to wrap up.
Yeah, I'm just going to go over my summary. So as I said, microburn is the first to start operation detector of the SBN program Fermilab. It is, being the first, of course, well, not the first large TPC, obviously, but the first large TPC of the SBN program. We have done a lot of pioneering work in, understanding the detector response, calibrating this detector response, as well as event reconstruction and of course, physics. But for physics, you should go to neutrino session. And the 2 results that I show here today is our novel technique for understanding space charge effects with data. And of course, our results in measuring and understanding the PMT gain over a large period of time. Thank you.
All right, thank you, Relitsa. Questions to Relitsa? I don't see any hands raised. I had a quick question on with the laser measurement on E-field. Can you tell us what level of precision was achieved?
I think it was a couple of percent.
Okay, 2% or so. Okay, all right. Thank you. Let's move to the next talk then. We have Stefania Bordoni talking about construction, installation, and operation of Protodune single-phase experiments.
Okay. Okay, I think you can see my screen. So yes. I will give an overview of the construction, installation, and operation for a Protodune single phase. So as you know, Dune is a next generation long baseline experiment in construction in the US. So we will have a neutrino beam going from Fermilab to South Dakota. And the fire detector will be composed by 4 independent modules of liquid argon TPC. So you just had a nice introduction about the technology, so I will not go through that. So the fire detector will be located 1 kilometer underground, and each of those modules will have very large dimensions that are reported here. So to go to this very large dimension, actually we needed to have some prototyping, and actually there are 2 prototypes of still large dimension that have been built and are operated at CERN, that are the Protodune detector. And I focus the talk on the single phase technologies. That is exactly what has been just presented for microboom. So we have a particle that will ionize, that actually ionize the liquid argon. That will ionize the argon, and the charge is detected on the anode plane, and then there is some light that is detected by photodetector.
Sorry, there is some, sorry, Stefania, I see other people talking. Is that, yeah, go ahead. I think I muted.
So Protodune also served for probing a new concept for very large dimension cryostats. So this came out from a collaboration with the industry. So this firm actually was developing and using this cryostat technology since 25 years for liquid natural gases transport in ships. And this technology has been re-engineered for liquid argon TPC detector to take into account the needs, especially all the openings that we have for the installation and also for the communication for the detector. So Protodune serves as a validation of this technology, and now this is approved and being used for several experiments like Dune, SBND, and DarkSide. Here below you have a sketch of how the insulation and this technology is composed of different layers, and a nice picture of the inside of Protodune during the installation, and you can appreciate the corrugated membrane that you can see here that is in contact with the liquid argon from the picture here. Coming to the detector, we have 2 drift volumes that are separated by a central cathode. So you have a picture here on the right, you can appreciate the cathode. And on the left, there are the anode plane that are composed by 3 planes of wire with a different orientation. We have also called electronics to minimize the noise. We operated the detector almost for 2 years. We have very, very high voltage stable condition during all the uptime, a very low number of bad or noisy channels, so less than 1%, and an excellent signal to noise ratio that is far better from the nominal design value. So here, for example, is this signal to noise ratio for the different plane. For the collection, the mean value is around 45, while the design value was 9. And also excellent large purity with a low value of impurity that is estimated less than 3.5 part per trillion oxygen equivalent. And so this corresponds to a very good electron lifetime, greater than 20 milliseconds, but even fairly higher for some periods. For the photon detection system, so they are located behind the wire, as you can see in the picture here. And there are 3 different designs that are installed and operated in Protodune. They are all based on light guide modules with a wavelength shifter and read by silicon array. We have a calibration system that is done by a pulsed LED light that is installed on the cathode. And with that, we can do some the calibration, as for example, they estimate the time resolution for 2 consecutive pulses that is estimated around 14 nanoseconds. On the plot here on the right, you can see the analysis of the light signal and track matching that is crucial for events in neutrino for dune. And you can see the very nice linear dependence for the matching between the flash and the tracks. Here is a slide to summarize the timeline for ProtoDune. So in less than 2 years, we came from the building the cryostat to operating it and collecting very nice data and with an excellent quality, like the 2 event display that you can see here. So we took data both with a beam particle, so coming from a dedicated beam line that has been constructed ad hoc from CERN, and also more than 1.5 years of cosmic ray data. We have also physics measurements that are in preparation, and there will be a talk in some other session. And also recently posted a paper on arXiv that is being submitted to peer-reviewed journal. Through the DAC, we have 2 independent readout method for the TPC. So RCE was the baseline based on the previous experiment, 35 tons, and Felix, a new design coming from developments for the Atlas collaboration. Then an independent readout for the photon detection system. And then the trigger and the timing system that collect information from the photon detector, the cosmic ray tagger that I didn't mention, but there is on the front and on the back of the detector, and from the beam instrumentation. And from those information combined, they built up the trigger. The DAC farm is composed by 20 high performance servers to control and monitor the data flow. And it also foreseen some temporary storage before the final transmission to the permanent storage like EOS at CERN or the data storage at Fermilab. Coming to the performance, so we did a careful data processing and calibration of the TPC signals to extract the ionization signal. And then, so from here on the right, you have a nice DADX for cosmic muons, data in Monte Carlo compared. And also we spend a lot of effort to understand the space charge effect that again has been introduced in the previous talk. So here is a very similar plot to what was shown before. So it's a top view of the ProtoDune detector. So the x-axis is actually the drift direction. So the 0 is the cathode and the z is basically the beam direction or the transversal direction. And so, and the dotted line here is the field cage. So the point, the blue point is the entry point of the cosmic rays. And so you can see some deviation at the edges and that are increasing going through towards the cathode. So this is the clear signature of the space charge effect that we had to take into account on our analysis. There is also nice information, calorimetric information that we can extract from the photon detection system as shown here. So here is the number of photons as a function of the energy of the electron beam. And you see the very nice linear dependence of those. We also monitor the overall stability of the detector response. For example, the collected charge along with the time. So here is the very starting day of ProtoDune, and here is close to the end. So you can see the rise up of the collected charge that this is related to the increase of the purity of the liquid argon, and basically a very nice flat distribution. Some drops coming from drop in purity, basically for some test on the cryogenic system as well. And also some other points to other tests on the hardware. Here is a plot on the electron lifetime that I was mentioning before that was basically higher than 20 milliseconds. So this is by the purity monitors that are installed inside the detector. And here again, we have some drop in purity due to some test, or here actually this big drop is coming from a lack of data. Also, the photon detection system has some stability studies. For example, in this case, I report for the gain, and you can see that along 100 days, these two systems are very, very stable. ProtoDune has also served for some R&D for Dune. For example, the use of xenon doping in liquid argon that it seems to get an increase on light yield and a better detection efficiency. So the aim of this doping in ProtoDune is to study the stability and uniformity of the response for a large site detector. To do that, in ProtoDune, we inserted actually three new photon detection systems capable to also detect xenon line or visible light. And there are studies that are ongoing, but a preliminary result that I show here is the ratio actually between sensor that can see only xenon light and both xenon and liquid argon light, and actually demonstrate that basically all the slow component of the liquid argon light has been converted to xenon light, reaching the plateau at 75%. We also tested the high voltage system beyond the design specifics to check basically the margin of operation and also extend some studies like drift velocity or space charge. So this was done by setting the high voltage higher of 30% of its nominal value. Here is a plot showing voltage and current. So we took data for about 3 days continuously, and you can see the stability of the system that is actually very consistent with the nominal conditions. Another test is using a neutron generator to actually test the low energy calibration scheme campaign for Dune. And this is done using neutron with 2,3 MeV. And the idea is to try to see if we can detect a signal from the gamma cascade after the neutron capture. So this is an event display. We had the neutron generator located on the top of one of the APA. And the idea is to see if we can detect higher activity of small signals in that APA with respect to the other two. So I pointed out those possible candidates by this arrow. And there is for sure, of course, more quantitative analysis that is ongoing to define if these are really signals coming from the neutron.
Stefania, one more minute to wrap up.
Yes, I need 2 slides. So also towards June, we had some developments from the DAC. So the Felix readout actually have been validated and chosen as a baseline for Dune. We also had development to put together a hit finder, so a real-time processing of different regions of interest, and to so detect online directly a region where there is an interesting signal, as shown in the figure. So here is the true signal, and this is what the hit finder can find on real time, and based on that, a software trigger. We also had some development to enlarge the readout window that is usually 3 milliseconds up to 1 second. So I conclude. We switched off ProtoDune just a few days ago after 2 years of really excellent data and excellent performances. ProtoDune has served as engineering prototype for cryostat design, cryogenic system, and also for the test of the assembly procedure, but is also provide excellent detector performances. And with that, we are preparing physics measurements that will be presented in next conferences. It also has served as playground for R&D towards Dune, both on hardware and DAC. And I leave you with this table that summarizes for some parameters the performance achieved by the single phase ProtoDune detector with respect to the specification that was actually the requirement for building the detector. And we are all looking forward to this ProtoDune 2 that will be a small scale of the first model of Dune. Thank you.
Right. Thanks, Stefania. Questions? Right. I actually had a couple of questions. The first one is for the neutron generator stats that are being done, there's also xenon doping. Would that absorb those neutrons, or what's the impact?
A quantification of that, we think we do not have it, but I don't see how they may interfere. So
oh, I was wondering the Z, you know, if neutrons get eaten by the due to the doping, but
I'm not aware of this problematics, honestly.
Okay. All right. Actually, in the interest of time, I don't see any other questions. So thank you, Stefania. So for the next talk, we have Dante Titani talking about performance of photon detectors in protodune single phase.
Okay, hello. Can you see my slides?
We do. It's not quite full screen, but I think it's good.
Okay. Okay, I will speak about the protodune single phase scintillator detector and the characterization and some calorimetric study of beam electrons. Protodune is one of the two prototypes for the Dune-Far detector. It's located at CERN, and it is at now the largest monolithic single-phase detector. It has a 3.6 meter drift region at 500 volt per centimeter, which makes it one of the most challenging large PPC ever built. The role of the scintillation light in the PPC is not even limited to spatial localization along the drift direction, but it can be used for trigger non-beam events as atmospheric neutrinos or supernova neutrino. And it can be used for calorimetry measurement, since half of the deposited energy is emitted through scintillation light. And as a last thing, we can use the light for an accurate signal attenuation, like to calculate the impurity in liquid argon or so. Light detector embedded three technologies, and which has to satisfy the geometrical constraint on the detector. The three technologies are arranged in 60 modules, arranged in 6 APA, so 10 modules in each APA. They are, of these 60 modules, 58 are light baths, light guides, and 2 are Arapuca modules. The guide technologies use the same principle to transport the light via total internal reflection. The only things after they have shifted the photons from 128 nanometers. The only difference is that the double shift use two processes to shift the light instead of the just one process. The light is transported at the end of the bar, and an array of photosensors is located at the end of the bar. For all the light guides, the configuration is 12 SIPM, 6 by 6 millimeter, arranged in 4 groups of 3 parallel connected. The SIPM used are Sencel and Hamamatsu. The Arapuca is a light trap. You use a decoy filter to trapping the light inside the box, which is reflected from the surface inside the box, and at the end, until it hit the photosensor located at the bottom of the box. All the Arapuca use 12 SIPM, 12 Hamamatsu SIPM connected in the parallel, and the only difference is we have 8 cells of one dimension and 4 cells of double area. The photosensors are full characterized using an LED, low intensity pulsed LED located inside, which is drawn inside the TPC through optical fiber. and good linearity and a lot of features are studied and measured, like gain versus bias voltage, breakdown voltage, after crosstalk, and so on. Once the photosensors are fully characterized, we pass to analyze the beam events to look at the photodetector response to the argon light from charged particles. For this analysis, only half of the TPC were used, since the beam is completely located in half of the TPC. In this side, we have just one Arapuca modules located in the first APA in front of the beam, and the other are double shift and deep coated bar alternated one by one. The particles produced by the beam are identified by beamline instrumentation and joined, which uses 7 curve detectors and time of flight measurements. Joined to this beamline instrumentation, we use the TPC reconstruction to distinguish electrons from pions, and the light collected analysis to have the last separation of the pi mu and k mu particles and some layer removal. Here there are 4 spectra, which just I put there for an example to show how appears the different particles. Here we have electrons, protons, kaons, and pions and muons together. As you can see in the kaons too, there is the peak of the muons. The beamline instrumentation were not able to distinguish these last particles, pions and muons, and but with the using the collected light, we were able to make this separation, since the pions stop inside the TPC, instead the muons after 2 GV, they from 2 GV to more energetic muons, they escape the TPC. So using a correlation between the light collected between the different groups of photodetector, we can make the separation, and moreover, we can remove the outlier as in the electrons on the pions and muons as the outlier generated by cosmic particles. Here there is an example how to appear the correlation between the 2 different group of detector, in this case APA 1 versus APA 3, and you can see the 2 groups of events, and here on the plot on the right you can see the 2 distribution, the 2 contribution to distribution. The same things can be made for the single particles and can be used to discriminate the outlier, to remove the outlier. In this case, it's an example for 3 GV electrons. Here on the right, the plot on the right, you can see the spectra before and after the outlier removal. Once we have the number, the photon detective per particles from all the detector, we can we use the electrons and muons of 2, 3, 6, and 7 GV of momentum to compare with the simulated photons. The ratio of them is used to evaluate the efficiency of all the modules. As you can see in the plot on the right, you in both plots, but you can see that the double shifted deep coated are similar to each other, but the 2 groups are separated by a factor 2. Instead, the Arapuca bar show a much higher efficiency. Moreover, in the bottom plots, you can see that the cells of the Arapuca, which have half of the area, have much more efficient than the Arapuca with a double area, the last 4 points. Okay. What we got from this number is an efficiency of more or less 2% for the smallest cell of Arapuca, 1% for the larger cell, and 0.2 and 0.1 for the 2 technology of BARTs. The Arapuca, since the Arapuca showed a good efficiency, we focus on the Arapuca and we start to study some calorimetric figures of the electrons produced by the beam. What we did, we just plotted the energy or the beam momentum of the beam on the left plot, and on the right plot is plotted the number of photons detected. The beam momentum comes from the beamline instrumentation. We fitted with a Gaussian both distribution, and we studied the linearity of the number of photons detected versus the beam energy or beam momentum, and the resolution versus the beam momentum too. As we can see, despite the data show a good linearity, a slight deviation from the linearity is visible. So what we did, thanks to the Arapuca granularity, we were able to make the geometrical correction due to the, even if small, but were present shift in the length, changing the length of the shower due to the changing in the energy of the beam. So even if the electromagnetic shower length is proportional to the logarithm of the energy, we got a good geometrical correction. And after this correction, we observed an increased linearity of the fit and of the Arapuca response. About the resolution, we analyzed the quantity, the spread of the photons detected over the main number of photons detected for each energy. We fitted the data with the standard equation for the resolution, and we were able to distinguish 3 contributes and figure out the source of all of them. For the stochastic contribution, that is the one that go with the 1 over square root of E, we identify it in the statistical distribution of the light produced by the Levi-Lacron, so the Boson, from the Boson statistic. And we can see from the plot that the stochastic spread for very good the component get from the first, for the resolution fit. For the noise contribution, which is the term that is proportional to 1 over E, we observed, we figured out that the source comes from the electronic noise of the readout chain of each channel. And in this case too, the signal over noise of the electronics match very good with the 1 over E component from the spread fit. And the last, the constant contribution comes from, we figured out that this contribution should come from the beam spread, even if in this case it's not perfectly matched each other, but most of the contributes come from the beam spread measured by the beamline instrumentation. Another contribution which can be summed to this contribution comes from a last uncertainty on the energy which the particles lose before to enter the TPC, which cannot be measured, but we got from a simulation a value which is around 2% that is compatible with the missing spread in these plots.
Dante, about half a minute to wrap up.
Okay. And the last things I want to show is just since the Arapuca showed a very good answer to the light, we replaced with just a simulation. We replaced all the PD modules with Arapuca and getting a value of 1.3 photon per MeV for beam electrons, which is much more light of what we want from the Dune requirement. These have made Arapuca the first choice for the Dune PD system. The proto-Dune will have a second run, and a new version of the Arapuca called the X-Arapuca will be placed in the 4 of the 6 APA of proto-Dune this second run. And after that, in conclusion, the excellent efficiency, linearity, good resolution, granularity of the Arapuca have made this detector the first choice for Dune. And together to that, the this have made have opened the way to reconsider the photodetector a performing second detector for liquid argon, and not only an adjunction to the TPC. Together to increase the TPC resolution, the Arapuca will play a key role in Dune for the low energy neutrino physics, like supernova and solar neutrino and other. Thank you.
Great. Thank you, Dante. Maybe we have time for one quick question. Okay. I had a question. You probably mentioned this. The differences in the efficiencies you showed for the different Arapuca salts, is that largely coming from geometry and coverage differences, or?
Yeah, because in principle, I told very fast, but we have a cell, two kind of cell. One cell with this certain window, another cell with a window that is double the first window, but the number of photosensors are the same. So we have a larger surface, but the same photosensor inside. Mm-hmm. So from a geometrical, just a features of the Arapuca.
Okay, thank you, Dante. Let's move to the next talk. We have next Mike Mooney talking about space charge effects in Proto-Dune SP.
I was muted. Can you see my slides?
We can see your slides. Can you go to full screen? I think this is okay, but if you can, that would be great.
Sure. Is that better, or you want me to go to presentation mode maybe?
Yeah, try that. If not, we'll go ahead with this.
Is that better?
Yeah.
Okay. Thank you for the introduction. I will be talking today about space charge effects at Proto-Dune. So you've already heard a little bit about Dune, the Deep Underground Neutrino Experiment, which is a neutrino oscillation experiment with a 1,300 kilometer baseline, makes use of a large TPC far detector, and there's also a near detector at Fermilab with a liquid argon component. So the main physics goals are to probe the P, M, and S parameters as precisely as possible, including delta CP, also making a statement on the ordering of the neutrino masses, and low energy neutrino physics like supernova burst neutrinos, and also beyond the Standard Model physics will be probed with this experiment. As I mentioned, the FAR detectors are large TBC detector modules and located at SURF, the Sanford Underground Research Facility, 1.5 kilometers underground. And these are quite large detectors, 18 by 19 by 66 meters for the cryostat, slightly smaller for the TPC inside of them. And en route to building these giant detectors, we have built two proto-dunes, one for both the single phase and dual phase technology, which you already heard a little bit about in the previous talk, at the CERN Neutrino platform. And these 1 kiloton detectors are placed in a charge test beam, and the reason for their existence is to test component installation and commissioning and performance ahead of the running of the FAR detector using identical full-scale components. So Proto-Dune single phase, which I highlight here at the bottom, you can see an inside view with the two APA planes on the left and the right, each consisting of 3 APAs, with a cathode in the middle and 3.6 meters in between the anode and cathode. So this detector has been operating since 2018, and the dual phase detector, which you've heard about, has been operating since 2019. So I'll be focusing on the single phase detector today and looking at a prominent feature in our data, looking at first cosmic data, and you look at the cosmic track entry and exit points that are plotted on the bottom two plots and two different views of the TPC of the Proto-Dune single phase detector. You can see on the bottom left where the cathodes in the middle and the two anodes are on the left and right. There's this transverse offset from the sides of the detector, the top and the bottom on the left figure, the front face and back face on the right figure on the left and right. These transverse offsets for charge originating the cathode is about 35 centimeters. And that means that you start at the edge of the detector near the cathode, and by the time you make it to your ionization makes it the anode, you migrated inward about 35 centimeters. And this is due to space charge effects. And we see them as expected given that protodune single phase is located near the surface. And the space charge is the buildup of slow-moving argon ions that are produced from cosmic muons that impinge the detector rapidly and near the surface. Of course, we get ionization that's that's spread out on the order of milliseconds. That's our nice images that we show with our detector. But the argon ions stay for minutes before they drift to the cathode, and enough of them pile up to make an E-field distortion that then leads to trajectory modification of further ionization deposited in the detector. So this is a pretty significant effect, and we can talk a little bit about the impact of the space charge effects on observables of interest. So again, the space charge effect leads first to E-field distortions that then lead to further distortions and reconstructed ionization position. And so you can get biases in the reconstruction of particles, particularly energies, in several ways. Non-energy impact is that the location of reconstructed charge is changed. And this is again due to the spatial distortions, like the track entry exit point distortion, inward migration that I showed you on the previous slide. You also get particle energies that are modified from the E-field distortions. I show you on the bottom left plot the predicted amount of E-field distortion due to space charge prior to detector running. We developed simulations to predict how much we would see. And you can see near the cathode, we have an upward shift of about 13% or 14%, the amount of E-field, or the E-field magnitude. And it dips close to 5 to 6% near the anodes. So this leads to different amount of electron-ion recombination throughout the detector, which leads to different particle energies from what we would expect. So in addition to that, you also have particle DEDX that's modified, and this comes in two different effects from both E-field and spatial distortions. The E-field from the same way as particle total energy from the recombination impact, but also you can have squeezing or stretching of the track along the direction of that the particle went through the detector, leading to the DX of DEDX squeezed or stretched, and that will bias DEDX, of course, as well. You see in the bottom right, the impact of space charge with in red and without in blue on positron DEDX near the shower start, which again, DEDX is used for electron photon discrimination, large TPCs. You can see a significant bias of that distribution due to this effect. So something we want to characterize in a detector and address in our calibration. And here I just highlight a little bit more explicitly how DEDX, again, is through recombination, is a function of the DQDX, the detected collected charge per unit length, and the E-field magnitude. And both the DX here of DQDX and the E-field magnitude are impacted in different ways by space charge effects. So now taking a look at first data collected with protodune. Again, we're looking at the same tracks, entry and exit points of cosmic data, looking on the left column with data, and the right column was the prediction that I showed you before, the associated E-field distortions. But what we're looking at in this view is a central, the top of the detector in the upper row, and the front of the detector in the bottom row, showing the transverse spatial distortion that one sees in either data or in the prediction. And you notice that looking at the left column and the right column, there's a significant difference between what we see in data and what we predicted. And this difference is about 50 to 70% larger spatial distortions near the TPC faces than we initially predicted. So we see up to 35 centimeters when we maybe predicted about 20 centimeters from the initial prediction calculation. So in addition to this increase in magnitude, you see asymmetries that are go across the cathode. So the upper left image in data at the top of the detector, the upper part, is the left drift volume, and the right part, the bottom part is the right drift volume. So the two different drift volumes. You notice that one side of the cathode has significantly less transverse spatial distortion than the other. So these asymmetries, which we don't include in the prediction, are likely due to impact of argon flow in the detector, which is not modeled. So we, after estimating robustly the spatial offsets of the TPC faces, which are 2D calibrations, we then move on to use a calibration method to predict the space charge effect throughout the entire detector. And this is by taking the 3D prediction that we have. We have a prediction of the spatial distortions throughout the entire bulk of the TPC in X, Y, and Z, and as well as the associated electric field. And we scale that spatial distortion map from prediction with the data Monte Carlo scale factors taken near the faces and interpolated throughout the entire volume. You see on the right here, if you know the top and then the bottom or measurements, so then you interpolate the kind of rescale the prediction in the middle throughout the middle of the detector. So then with that 3D spatial distortion map in hand, it's simple to then calculate the local drift velocity everywhere which I give you a reference from a study at Microboom that developed a method to do this. And then with both that local drift velocity map and a drift velocity model, meaning how velocity depends on electric field, which we have from previous measurements of, say, Icarus, which operated at the same E field, 500 volts per centimeter. We can then extract the E field distortions as well throughout the entire detector in 3D. So that last step, the E field distortion results I show on this slide, comparing data to Monte Carlo on the right, which is just taking the prediction and including it in our Monte Carlo simulation. And you can see that we also have an asymmetry in predicted underlying E field, as we would expect from an asymmetry in the high level spatial distortions that we observe, where again, the central vertical line is the cathode, and then the two sides, left and right of the plots, are the two anodes. And in between them, 3.6 meters of drift. You can see that the E field in data goes up to about 25% higher than the nominal E field of 500 volts per centimeter near the cathode at maximum. So that means that the E field near the cathode is greater than 600 volts per centimeter. So this is something that we need to certainly address in our simulation and reconstruction. We address in simulation by taking this new data-driven map and putting that into an improved Monte Carlo simulation, which is used in all the results presented at this conference, and also in a paper we just put to archive that will be published in JINS soon. In addition to that, we also want to calibrate. We don't just want our simulation to match data. We also want to calibrate to get better performance in both simulation, now close to data, and data. So one case study on a type of calibration that we've started looking into is a correction of the particle DEDX. I mentioned this before, that DEDX is impacted in multiple ways by space charge. And it's important that we have a unbiased and as precise as possible estimate of DEDX versus residual range, distance from the end of a particle track, because that's very important in particle identification. So that's how we identify muon versus proton versus kaon, and also electron versus photon by using the beginning of showers. So we correct out separately those two impacts of space charge effect with the data-driven calibration spatial distortion map and associated E-field map by correcting for the spatial squeezing and stretching of reconstructed charge, which I show on this slide, which impacts the DX in the calculation. So we kind of unstretch or unsqueeze the charge with our calibration map in hand. And then in addition to that, we make a correction due to the E-field dependence of the electron-ion recombination. Again, the electron-ion recombination is an effect that will take, you have a certain amount of charge that is deposited due to the ionization energy of argon in your detector after a particle passes through. And then immediately before any drift occurs, you'll have some significant fraction of that charge which recombines with parent argon ion or nearby argon ions. And this leads to something like between a 25 and 50% decrease in the amount of charge. But that's also how much you get. It depends on the local E-field magnitude. So here we basically make a correction for that effect with the E-field map in hand as well. So then we take the results of the DEDX calibration and apply it to our beam data. We also apply this to cosmic data, but Richie Dierba will show in his next talk some comparisons with cosmic data. And I should note that all plots that I show in the next two slides, that additional energy scale calibrations are included in these plots that Richie will also discuss. But what we're looking at is DEDX versus residual range for beam stopping muons, and for data on the upper left, and for Monte Carlo with the data-driven space charge simulation included on the upper right, compared to expectation from theory, so Landau-Vavilov theory. And you see that there's a very good lining up between the both data and Monte Carlo and the associated theory. And then looking at the bottom and in the plot, you can see a direct comparison between data and Monte Carlo, including this data-driven space charge map. And we see very good agreement as well after this, this calibration is applied.
1 more minute to wrap up.
Thank you. So I should note, again, other energy scale calibrations go in here, but if you did not correct for space charge, certainly, no matter how many other calibrations you apply, you would not see good agreement given the magnitude of this effect. So likewise, we looked at beam-induced protons, which you can see the same comparisons, data to theory on the upper left, Monte Carlo to theory in the upper right, and data to Monte Carlo on the bottom, a 1D projection. And in all cases, you see quite good agreement after the calibration is applied. So it looks like our DEDX calibration with initial data-driven map is performing quite well. So to summarize, we presented a first measurements of space charge effects of protodune, very significant effect due to the detector being on surface, up to 35 centimeters of transverse spatial distortion, the TBC edges, Also, the E field distorts as large as 25% of the nominal E field near the cathode. We presented a DEDX calibration, which seems to be performing well. These results are summarized in a forthcoming paper I list here in the archive link, which we're submitting to JINS this week. And we're also preparing a dedicated space charge publication, including improved 3D calibration, not just a 2D projection, but a 3D calibration directly in the bulk, systematic uncertainty analysis, and time-dependent studies as well. Thank you.
All right, thanks, Mike. Questions? Okay, well, people are thinking to raise their hands. I'll ask a quick question, Mike. Can you comment on the time dependence of the space charge effects, and also, now that there's at least 2 surface detectors, how the measurements compare across them?
Sure. So I can comment a little bit first about the time dependence, which is a very good question. And referring back to just looking, say, at the top of the detector in the upper left in data. So what we've seen over a year of running, and we've run for longer than that. Preliminary studies just looked at 1 year of data. We saw that the beam left or above, on one side of the cathode, there was very little change over time, but on the other side, where it was larger to begin with, it decreased significantly over time by as much as 30 or 40%. So there's a significant time dependence shown here at ProtoDune. I can also report that at Microboom, we have a paper coming out on archive this week, actually, about space charge effect studies done there. And the time dependence there is shown to be over 3 years, about 3 to 4%. So dramatically different in these 2 detectors. And it could be that there's significant dependence on the liquid argon flow patterns in the detector. The cryostat design could be playing a role here. More public results on that in the future. And for the comparisons between single phase and the dual phase detector, due to some initial issues with the high voltage system at the dual phase detector, this hasn't been quite studied in detail substantially yet. But these issues have recently been addressed, and we expect that we'll have a statement on space charge in our next round of results for the dual phase, probably certainly within the next year, if not sooner than that.
Okay. All right, thank you, Mike. Okay, with that, let's go to the next talk. Next, we have Richard Durba talking about energy calibration in ProtoDune SP.
Hi, thanks to Janya. And this is as large as I can make it, so I apologize. I wish I could make it larger.
This is pretty good.
So I'm going to talk about energy calibration, which is specifically the DEDX. So just to jump in, so we're a test beam experiment, mostly measuring protons, muons, and pions. And our big push is to really understand how these particles stop, which means we need to know the DEDX. So what we use is the modified box model, which kind of originated in Icarus when they took the Burke's model, and then Argonaut measured the recombination parameters in this sort of modified model. And that's how we got what is commonly known contemporarily as the modified box model. And it's this equation here where the calibrated DEDX is a function of an exponential of dQdx, a bunch of constants, and then minus our recombination parameter, so our alpha in this case. And what you'll notice is the work function, W ion, rho, alpha, and beta, are all constants that we could measure, rho being the density, alpha and beta being stuff associated with recombination that Argonaut's measured. But there are 3 things that we need to understand, which is dQdx, our gain calibration, which I'll refer to as CCal, and the local electric field. So I'm going to go on how we measure these and how we get a calibrated DEDX. So the reason why we need to do this is kind of displayed by this flow chart. So when we get ionized electrons from tracks traveling in liquid argon, we get basically electrons per centimeter. And these electrons per centimeter will drift to the wire planes. And as they drift, they're impacted by things like impurities in the liquid argon that cause electron attenuation, diffusion, basically the drift electrons spreading out, the space charge effect, which Mike gave a really good talk explaining, and recombination, these electrons basically saying, I want to couple up back with a positive argon ion. So after they drift, they will experience all these effects, and then they're going to get to a bunch of wire planes where they'll be right out at the anode plane array. And there are more effects because you have these stationary wires. There's going to be field response effects, and then the ADC physically has to do the electronics to measure an ADC times a tick per centimeter, which is our dQdx value. So we have all these effects, and then at the tail end of that, we then calibrate dQdx as a function of X, Y, and Z using what the ADC reads out. And then we provide a gain calibration, and then magically from that, we get our DEDX as a function of mega electron volts per centimeter. So I'm going to kind of work you through how we get there. First, starting about the electric field. So as Mike just beautifully stated, because of the fact we're a surface detector, we see positional and electric field distortions that need to be calibrated out. The way we do this for our DEDX measurements is we take the local electric field using the space charge effect calibration map for a specific calorimetric hit. Another thing we do is there's going to be squeezing and stretching of each step length as we move wire to wire. So we use the map to also correct for that. And just as kind of a general guideline, the kind of baseline electric field that we measured was 0.487 kilovolts per centimeter. This differs slightly what the spec was, which is about 500, but it's pretty spot on considering everything. So let's kind of dig into the nitty gritty, which is the dQdx calibration. So this is probably one of the most involved sets of our calibrations, but it's completely necessary. And the way we calibrate everything is we take muons at high residual range, and we do this because we know their uncertainty at high residual range for DEDX within about 1%. So these are pretty good standard candles. And now for calibrating our dQdx, we take cathode crossing muons, which have a well-defined T0. We cut out muons with specific track angles, which could kind of fuzzy out our responses. So if you have a track angle that's at 90 degrees, well, your collection wire is at 90 degrees. So there's going to be some sort of detector effects that you're not trying to measure with your dQdx calibration. So we make these cuts to make sure that doesn't occur. And then the first thing we do is we measure the fluctuations as a function of YZ. And then we measure the same thing as a function of X. We normalize dQdx as a function between the drift volumes because Protodune has two drift volumes with the cathode separating it. And then that's how we get our calibrated dQdx. So what you're seeing on the right is a plot of our track angles. And so this is what our track selection population sort of looks like. These are all cosmic muons. So they're going to have a specific angular dependence, i.e. they're all going to be mostly pointing downward. And the XZ is going to be somewhat isotropic. So the way we do this is we apply each step to the one previously. So we start with our YZ calibration. And this is really important for kind of calibrating out any sort of detector effects like gaps between the APAs. So we take the dQdx for the global sample, and then we basically divide that by the dQdx for our specific YZ voxel. We take that, then we apply it, and then we do our X calibration. And what this calibration does is it's trying to calibrate out diffusion and electron lifetime. And again, we do the same exact steps. And that plot you can see right here, you can see that as we move further and further from the wire planes, which are on the ends of this plot, we get a reduction in dQdx. So we want to flatten this out with this calibration. And then the last thing we want to do is normalize everything so that the two APAs planes have similar responses. And then we basically multiply all this together when we actually apply our calibration. So our dQdx calibration is the calibration of X, the calibration of YZ, times this normalization factor to normalize between the two drift volumes, and then finally our dQdx. And what you're seeing in the bottom right-hand plot is the uncalibrated dQdx and then the calibrated dQdx scaled as such. And you see that the peak is a little bit sharper. So you definitely see a physics benefit by calibrating the dQdx, besides just it's what you need to do to make sure that from wire to wire, you get the same response. The last thing I want to talk about is the gain calibration, which I'm going to call CCal. And the purpose behind this is because we know the DEDX of muons at high residual range so well. You see it in this flat line right here in the Landau-Vavilov curve. We can really pinpoint what our CCal should be based on that. So what we do is we take the same cathode crossing tracks, but we necessitate that those cathode crossing tracks need to stop within the fiducial volume of the detector. And we also make the same angle cuts as we did before. the next thing we do is we remove tracks that have some sort of difficulty with them. So that could be broken tracks broken up by the detector. That could be tracks in which the reconstruction says there's a Michel electron attached to it when there shouldn't be, which leads to problems with the residual range. So we remove those tracks. And then the last thing we do is we take high residual range, which is about 120 centimeters from the stopping point of the muon to 200 centimeters at the stopping point of the muon. And then we measure the dQdx for those values, and then we can compare it and scale it up based on the expectation curve. Just for a warning, the way we do this, we need to set a benchmark because everything could be arbitrary. So what we try and do is we try and say that the CCAL should be 5 times 10 to the negative 3 ADCs times tick per electron. So we measure that sort of calibration, and that's how we kind of benchmark everything between Monte Carlo and data. So for the run you see in the bottom left, you see that the measurement is 5.4 plus or minus 0.1 times 10 to the negative 3. So that means that there are detector effects that are causing us to stray beyond that 5 times 10 to the negative 3 that we would expect from a perfect detector. So as you can see, once we fit everything to data, you see good agreement between the expectation and then the DEDX. And then once we applied the CCAL, we then see that data in Monte Carlo has good agreement where every single black data point kind of is mirroring its red Monte Carlo constituent. So that's kind of the soup to nuts, how we go from just simple measuring a hit charge to measuring our final energy calibration. So what we do overall as a recap is we measure the electric field, we make sure that the dQdx is flattened out, and then we measure a gain calibration to convert it from our ADC to our mega electron volts per centimeter. And as a final say-so, I will again point everyone to the archive paper that we recently put up on our Protodoom performance, in which all these plots and some more are included. And the last thing I want to leave you with, and a metric of how well we're doing, is our separation determining what's a muon and what's a proton. So on the left-hand plot, you see the DEDX for stopping muons and stopping protons, and you see that there are clearly two populations. But the next question is how well can we determine where these two populations are? And that's what you can see on the right-hand plot, which is a likelihood plot in which we basically just take a chi-squared divided by degrees of freedom. And you see very good separation between a proton, which is that red curve, and a muon, which is the blue curve. So it means that our DEDX curves are working very well, and we're hopefully going to publish some hadron cross-section and some more Bragg peak analyses with these improved calibrations. And that's kind of all I have.
Right. Thank you, Richard. Questions to Richard? Richard, maybe quickly you can comment on the improvements planned on this.
Yeah, so right now we only looked at a few select runs. So we're currently integrating a calibration database that would allow analyzers to look at any run they want across any beam spectrum. So that's going to be one improvement, in which we're basically taking this calibration and scaling it up for all test beam data and some cosmic data. So that's kind of the most important improvement that's going to be made. And another improvement is this database will kind of normalize all the methods, so analyzers won't have to do it offline. So the improvements aren't as substantial as what Mike presented of doing an in-bulk calibration, but they're going to have definite improvements in normalizing our analyses and ensuring if you have a 1 GeV test beam run or a 6 GeV test beam run, you'll be able to calibrate DEDX.
Thank you. I see Stephen has his hand up. Stephen, go ahead. Let's see, Stephen, if you're talking, you're muted.
Sorry, apologies.
Yes, I'm here.
Can you say what zeta is in this slide?
Yeah, it's a chi-square divided. It's a chi-square divided by degrees of freedom between the DEDX expected and the DEDX measured.
Stephen, do you have a follow-up comment or?
No, I will ask Richie to explain that later to me.
Okay. I'd be more than happy to, Stephen.
Yeah, thank you. Nice talk.
Thank you. Okay.
Right.
All right. Thank you all.
Thank you. Okay, with that, let's go to the next talk. We have Sen Kwan talking about the MCP-based large area PMTs for neutrino detector.
Yeah, thank you for giving me a chance to report our status of the large area microchannel plant PMTs for neutrino detector MCN from ICHEP in China. My slide will be divided into 4 parts. First, the motivation of the new MCP PMT, and then the research and development of the 20-inch PMTs for Juno. And totally 50 kilo pieces PMTs mass production, and the bench test result will be described in the third part. As the last is a new design for the very, very fast 20-inch PMT for new requirements of the other physics, for example, the lasso, and maybe later for the hyperk and so on. The motivation many years ago, at least 10 years ago, the neutrino experiment in China with the diabase and get the result from good result. At that time, we use about 3 kilo pieces 8-inch PMT from Hamaso, but for the second generation Juno, at least 20 kilo pieces 20-inch PMT. And also, for the requirement of the physics, we need the detect efficiency, PMT detect efficiency at least 2 times than the Euro 1 in the market, supermarket. The Hamasu 20-inch PMT was only about 15% detect efficiency. So at that time, we just think about, is it possible to produce a new MCP PMT? We can see that this is, there is 2 types of amplifier for the electronics. Maybe first is the diode part, when the light come into the photoelectrodes, and it will be amplified by the diode part. And this is the MCP modules. What's wrong? And this is the MCP modules. The electric will be amplified in the channels. And for the diode part, there is a small MCP, small PMT with the timing resolution is good, and also there was a large 20-inch PMT. And at that time, there was still MCP PMT with 1-inch and 2-inch, but there was no 20-inch PMTs with MCP modules. So the ICHEP researchers have just a new design that to use small MCP modules instead of the large diode part, so that we want to use a transmission and reflection photocathode together, and maybe there is a high QE photocathode, and also we want to decrease the cost of the PMTs. So we have the design, and we need to have a project team and a collaboration group. We collaboration with the PMP company, the other institute and university and factories together to have a collaboration group. We call it the microchannel plant-based large area for the PMT collaboration group. And our leader was Yifeng. Also, he is the leader of the ICHEP. So we have a design, and we need to know what to do next. For the PMT, we know that there is a 4 core technology need to be developed to produce this new type of PMTs. First of all, we have the electro-optical to design the right situation for the constructor, and also the glass shell. We need the glass shell should be the low potassium glass, and also the MCP modules should be very high gain and low noise, and also the high QE photocathode together. Totally, we have the small prototype from 2-inch to 5-inch and to 8-inch, and finally, 2015, we have produced the 20-inch PMTs, and also we need time from the 2016 to 20. In 4 years, we have already improved the QE and also the collecting efficiency of the MCP modules together. For example, this is the MCP module. could be amplified the electronics, photoelectronics from the photocathode and then generate the large signals. And then we, at the beginning, we have the vertical 4 MCP modules here, but a lot of problems occur during our production process. So we have changed our version. This is the final version. So what's this is the final version for the vertical 2 MCP module. It is enough to collect both the whole areas photocathode to generate the photoelectrode together. And the glass shell, we need the non-potassium glass, and we can see that this is the this is the union and the potassium and together. We can see all the radiation background was controlled during the mass production process. And this glass bulb was manually borrowed by the skilled workers in China. It is amazing that men could manually to borrow this glass. And about 20 kilo pieces glass was produced manually in the last 7 years. And the MCP module that we need the collection efficiency from at the beginning, there is only 70% collection efficiency for the traditional MCP, and then with a lot of technology to improve its collection efficiency, finally use the ALD atom layer deposition to produce the special films on the surface of the MCP module, and we can improve the collection efficiency from 170% to 100%. The QE is very important for the prototypes. At the beginning, we have only a technology to produce the 25% QE, and then improve it to the 30%, and finally improve the 30% to 35%. All of the photocathode, no matter the 30% or 35%, all the biaxial photocathode, and whose peak wavelength is about 400 nanometers, just like the super biaxial photocathode from the mass of the SBA. We have the maybe the different technology process, but the same result for the photocathode. And after we successfully produced the prototypes for the 20-inch PMT, and we got the order from the Juno about 50 kilo pieces. So we need 1 year to make the mass production line and then have the mass production process. So the first mass production line was set up in 2016. 1 year later, and it can start the mass production and the bench test 2017. And we can see that every month, we deliver about 336 pieces of PMT from this is the company in Nanjing, and the Juno set here, and Beijing here. We just buy this is the large truck to buy the 300 pieces of PMT from Nanjing to Juno. And next month, 8/7, the last delivery time will be finished. We will be produce the total 50 pieces of PMT for Juno. And we can see that the performance of those PMTs. First, the anode part. Anode part is important for the single photo spectra. We can get the single photo spectra to get the P2 value and the high voltage and also anode resolution. We can see that the P2 value average delivery time was larger than 4. This is the data in the contrast, and the voltage was controlled less than 1,900, and also the anode resolution was controlled less than 35%. And we can see that the quantum efficiency of the 20-inch PMT mass production time, we can see that there is increased time from here. So QE was improved 30% to 35%, and also the relativity detector efficiency was also improved at the same time. This is because the collection efficiency of this MCP modules was about 100%, near 100%. And also this is the uniformity of the surface of the 20-inch photocathode. We can see the uniformity was controlled less than ununiformity was less than 10%, and the average date was less than 8%, is controlled successfully. As the time resolution for this PMTs was not good because we need the high detection efficiency, and the time resolution was not good for the TTS. From the prototypes, about 10 nanosecond was increased to 20 nanosecond, and also, but the read time was very fast, about 1.4 nanosecond, and the fall time also was a slow one, about 25 nanosecond. The aging behaviors of the MCP module was good. We used one PMT in the dark box with the highlight to training these PMTs, and the output current, we can see that the gain was decreased only 10%, and the single P gain was changed about 30%, but the output charge was about 40 coulomb. It is enough for the Juno to work out 20 years. And this is the aging behaviors of the MCP PMT was requirements the Juno's 20 years operation. And also the after-pass ratio is also was changed because for the low QE prototypes, there was the time distribution was only about 5 microsecond the peak. But nowadays for the 35 new high QE prototypes, we can see there was 1, 2, 3, 4, 5 peaks. Different peaks have the different reasons for the PMTs, for the backscattering electronics, or also the different oil in the vacuum tubes. But the total number is different. After-pass ratio was only about 5.25%, and the low QE part, this is only about 22%. But for the high QE, the technology was changed. The after-pass ratio was increased to 5%. And this is the table conclusion that for the compared to the prototypes, our 50 kilo pieces PMTs, the average data was for example, the QE about 32%, and the detection efficiency was nearly 32% at the 400 nanometers. And also the TTS, we can see that it's not good, 20 nanosecond, and the dark noise was also improved a lot, a little, and the after-pass ratio was 5.2%, and all of them was low potassium glass. Yeah, after we produced the 20-inch PMTs for the Juno, we have the production line, and we have a new design for the PMTs. We can see this is a. Yeah.
1 more minute to wrap up.
Okay. This is the new design. For we have changed the focused electronics. We can see that from this is a barrel bar, this is flower, and we can see the time TTS was improved a lot from the 20 nanosecond to the 4 nanosecond, but the collective efficiency was a little changed. And this is PMT was successfully used in the LASSO law in China. We can see that the data was about QE about 27%, and the TTS was 5 nanosecond. And so this is summary. We could successfully produce the 8 or 20-inch MCP PMT for the good single PE and the high QE, and better collective efficiency and uniformity of the detection efficiency. So, and also we try to improve our design, the prototypes for the other experiment. That's all. Thank you very much.
Right. Thank you, Sain. Questions? Sain, when you're talking about the new design, I think on slide 21, can you tell me what aspects of the design were changed that led to the improvements?
Yeah, this is a good question. Because for the preliminary design, when you use the Juno, we use all the surface of the photocathode, the reflection and the transmission, and also the focused electron was smaller. But for this and also the third part was the MCP modules. We have the ALD MCP modules with the high collective efficiency 100%. But for the this is new design. We do not use this part photocathode, only use this for this transmission photocathode, and also the MCP module was changed, and the focused electrode was improved a lot. So totally, the TTS was smooth and was good, but you can see that the collecting efficiency was decreased, and only 85%.
Okay, Thank you. All right, I see no other questions, so let's move to the next talk. Next, we have No Roy talking about the performance of solid reactor neutrino detector.
Okay, is everything all right?
Yeah, go ahead.
Great. So thanks for the opportunity to present SOLID's detector and the latest results on its calibration. So I'll first talk about the physics motivation behind SOLID, then present you the detector, the work we've done on the calibration, and the future prospects. So SOLID was designed to answer two main observations. The first one comes from the reactor antineutrino anomaly and the gallium anomaly, which both show deficits of neutrino and antineutrino at short baseline. These deficits could be explained by an oscillation into a light sterile neutrino state. And among several isotopes, uranium-235 might be the primary contributor to this reactor antineutrino anomaly. The second observation is a distortion in the reactor antineutrino energy spectrum, also called the 5 MeV bump. And that distortion might be linked to some nonlinearities in the energy responses of the detectors. And that's how SOLID was built, a very short baseline reactor antineutrino experiment with a reactor core enriched in uranium-235 and with an expected linear energy response. The interaction we are looking for in SOLID is the inverse beta decay, an antineutrino interacting with a proton to give a positron and a neutron. We then look for a spatial and time coincidence between the two particles, and we do an energy measurement of the positron. Due to the reactor core proximity and the low overburden, we are facing atmospheric and reactor-induced backgrounds. To answer to that, we've built a highly segmented PVT detector, and that will allow us, through the exploitation of the signal topologies, to reduce the background that can mimic the IBD signature. Furthermore, the PVT is expected to have a linear energy response. However, this comes with challenges because, well, it's a new technology to understand and qualify. And well, we have a lot of detection cells, and that means that we will need to have an extensive calibration to, well, to attain a good detector uniformity and to calibrate all those cells. Furthermore, tagging the gammas from the annihilations of the positrons will be a hard task. The detection cell itself in SOLID is made of one PVT scintillator cube. So this is for the neutrino target. And this is what allows us to have a big segmentation in SOLID. Each cube has two inorganic lithium-6 ZNS scintillating screens in each site, well, in two sites. For the neutron detection, the neutron will be after thermalization captured by the lithium-6, and then we'll have a ZNS scintillation. And each cube is optically isolated with Tyvek layers. The signal will be then read out by 4 wavelength shifting fibers connected in one end to an MPPC and in the other end to a mirror. And we'll look at this type of signal, first prompt signal from the PVT scintillation, so a large amplitude peak, and then a series of peaks from the ZNS scintillation. SOLID was designed as a modular detector with 5 modules of 10 detection planes each, and each plane has 16 by 16 detection cells. So that's how we get this, this high segmentation. The detector is integrated in a cooled container for MPPC dark noise reduction. You can see here a picture of SOLID inside its container. And we have a shielding for fast neutron passivation. All the environmental parameters are monitored constantly with sensors inside and outside this container. The construction of SOLID finished in 2017. And then after an integration and commissioning phase, we started to take data in May 2018. You'll see more about these physics data results in a talk from David Enaf Thursday morning. Due to the large number of detection cells and the sampling frequency of around 40 megahertz, we have a high data rate. And that means that we need trigger strategies and zero suppression threshold to reduce this data quantity from 2 terabits per per second to approximately 200 megabits per second. We developed a neutron trigger algorithm, neutron trigger based on a peak counting algorithm, which allows us to have a spatial and time coincidence between the prompt signal and the delayed signal from the neutron. And that allows us to have an unbiased and low threshold prompt signal detection. We have two other types of triggers, a random trigger for a calibration purpose, and a high energy trigger for high energy deposits and for muon rate monitoring. So the muon as we know, the muon rate is correlated to the atmospheric pressure, as we can see in the first plot. So that means that our background will depend on the environmental conditions. And so we need to monitor those continuously. For instance, here we have the temperature variation. We can see that the temperature varies at a 5% level between day and night. So this is a good sign for the MPPC response stability. And we also monitor all different types of triggers, the ZNS trigger, threshold trigger, the muon rates, to understand the sources from our background. For instance, for the ZNS signal, so the NS rate, we can see that it's not correlated to the reactor operations, but it seems to be highly correlated with the radon rates, the airborne radon rates concentration. So that means that, okay, this will be a source of background that will need to be understood and monitored carefully. So for the calibration in solid, we use an automated system. We have 6 gaps in the detector, so 1 gap every plane, in which we can put radioactive sources. And each gap is used to calibrate plus or minus 5 plane around. So that means that we will need penetrating sources. So we have gamma sources, cesium, bismuth, sodium, and americium beryllium. And we have neutron sources, californium and americium beryllium. Calibrating this detector, as I said, is a big challenge because we have more than 12,000 detection cells, and each cell is linked to different, to different MPPCs. And in the end, that makes more than 20,000 parameters to measure, to understand, and to correct. Furthermore, the cube signal, a cube signal combines a signal from 4 fibers. So that makes it difficult to decorrelate the cube effect from the fiber effects. And since we have cubes that are sharing fibers, well, we will have correlations between the cubes to understand and to correct. So first, we did a neutron calibration with the americium and the californium sources, americium beryllium and californium sources. We can see that we have a pretty good NS-ES, so electromagnetic neutron signal discrimination. We have an efficiency of neutron efficiency of 74%, an average in the detector, and we have a pretty good agreement between the two sources we used. And in the end, we have a relative module to module detection efficiency within 3%, 1% for the first 4 modules. We also did an energy calibration, so using the gamma sources, but we didn't have access to the photoelectric peaks. That means that we need to fit the Compton edges. So we developed 2 methods to determine the light yield and the energy resolution. The first one is a Klein-Nishina analytical fit based on the Klein-Nishina cross-section. And the second one is a Kolmogorov-Smirnov test, where we compare the data and the true Gen 4 energy distribution numerically convoluted. We also measured the channel parameters, so the MPPC gains are equalized at a 1% level. We measured each individual fiber attenuation, so you can see an attenuation pattern here. And we measured the fiber to MPPC optical coupling. You have here in the bottom plot plane, so the light seen by each cube in a plane. And you can see that we have disparities between the different rows. You have this row here that sees really less light than the other, meaning that it has worse coupling than the others. In the end, all the cube light yields were calibrated with a 3% precision. After all this correction, we attain a 3% light yield variation within a plane and below 5% light yield variation module to module. We've assessed the linearity at a few percent in the 0.5 to 4 MeV region. And we have a mean light yield of around 96 PA per MeV, which leads us to energy resolution as a stochastic term of 12% at 1 MeV. So to qualify this energy calibration, an important work has been done on the data Monte Carlo agreement. So we could use the calibration sources. So for the data Monte Carlo at low energy, we use the sodium sources. And we can say that, okay, we have a data Monte Carlo agreement within 5% in the 0.2 to 1.2 MeV region. And we also used our internal background. So we have bismuth induced background that comes partially from the radon decay. So the bismuth, okay, so this background can mimic the IBD because we have a prompt signal with the beta minus and then a delayed alpha that is emitted, which mimics the NS from the IBD. So that allows us to, okay, have an energy data Monte Carlo energy comparison at higher energies, and to have to test the topologies that we created in Solid. So basically the space distribution of the annihilation gammas from the positron. So we could test those and have a relatively good data Monte Carlo agreement on those two. Then we started recently a systematic study. So to assess the light field systematic effect on the reconstruction, on the energy reconstruction. So to do that, we created fake IBD simulations, varying the light field for each cube within 3%. And then we did a comparison between the nominal experiment and the fake experiments. In the end, with the assumption of a signal of a background of approximately 1, and with approximately 1.5 years data, we can see that the light field uncertainties already fall, the effects of the light field uncertainties already fall into the effect of the statistical uncertainty of the energy spectrum. To finish, we did a detector upgrade. So we started a detector upgrade this summer. We wanted to upgrade the generation of the MPPC. So for that, we started the upgrade in July 2020. And we expect we expect to have a recommissioning in September and then take 1 year of data with this new with this new situation. It will allow us to have a higher light detection rate, a higher light detection of around 40% in the same conditions. So that will be good to tag the annihilation gammas. And I think already at 12 minutes, so I'll let you with my conclusion slide.
Great, thank you, Neil. Questions to Neil?
Yeah, actually, it's Noe, but it's fine.
No way. Thank you for correcting me. Yeah, I was wondering about that. I was going to ask, you talked about systematics. Do you see in the end your statistics or systematics limited, or what do you expect to be your dominant systematics?
So for now, in the state we are not at this we're not yet at these assumptions with a signal of a background of around 1. So for now, I think the most important systematic that we have will be the statistical systematics. But then we didn't yet do the assessment of all the systematics that we can have. But I think now the main systematic of importance are the statistical one.
Okay. All right, thank you. So that's the last talk of the session. Thanks to all the speakers, great set of talks. We'll take a 5-minute break from now. So we'll reconvene in about 5 minutes. Thanks, everybody. So Stefania, you're going to take over the next session, right?
Yes, can you hear me?
Yes, I can hear you.
Okay. I also checked my video. I think you can see me. Yes. Yeah. Okay, very good.
Hi, so I think this is Cameron.
Hi, Cameron.
I'll be the first speaker. So good that you can hear me already. And I guess I'll start sharing my slides for when we reconvene, if that's all right.
Sure. Okay, I think we all can see your slides.
Okay, I'll just try to go into full mode and hopefully this doesn't vanish. No, it's vanished.
Okay, now it's perfect.
Okay, that is good.
Good, thank you. Is there any other speaker who wants to try sharing? I also see you now, Cameron.
Okay, I can never tell if my camera's going to work or not.
It works. So Stefano, Maciej are connected, Martina is connected, Federico is connected, Peter I've seen already before, yeah, and Felix. Okay, so all the speakers are there. Let's wait 2 more minutes, then we start. So I think we can start the last part of this session. So my name is Stefania Beolet, and I will be the chair of this last session for today of track 12. And we're gonna have another 7 interesting talks. We start with Cameron, who is going to present the S-Phoenix experiment at RIC. So Cameron, stage is up for you.
Okay, thank you. So yeah, as you're saying, I want to present the current status, design, and outlook and reach, of the S-Phoenix experiment at RIC. So I'm going to have a few topics I want to discuss here, but moving quickly in. So what is S-Phoenix? So S-Phoenix is designed to be a successor experiment to the Phoenix experiment, which last took data in 2016 at Frick. It's located at IP8, which is the same as Phoenix. And the aim here is that the S-Phoenix detector will start data taking in 2023. So we're at quite an advanced stage of design, construction, simulation as well. So this will be one of the next generation heavy ion experiments that we have and will be complementary to the experiments that are conducted at the LHC. So as a successor to Phoenix, kind of a good question to ask is, what are we reusing from Phoenix? And so here is a photograph from this year of the Phoenix experimental hall. And you can see that we've taken out the entire detector. And actually, on top of this, we're also replacing the beam pipe, which you can see in this photograph. But what we're really reusing is we have many years of experience of lots of good Phoenix physicists and engineers, and the infrastructure as well that existed from Phoenix. And we've also brought in a lot of new physicists and engineers from different experiments as well. So what is S-Phoenix? So unlike Phoenix, S-Phoenix is a barrel detector, which covers the full 4 pi. It still has the same center of mass energy collision from RIC at 200 GeV with a trigger rate of 15 kilohertz, but it's set in several different layers. So currently our design, we have 3 tracking layers. We have an inner vertex detector, an intermediate tracker, and a TPC, a compact TPC, and I'll give some more information on these as well. And then for our calorimetry system, we have an electromagnetic calorimeter, and we have an inner and outer HCal on either side of our superconducting magnet, which is actually the magnet which was used in Babar. So this experiment has a radius of about 270 centimeters and covers a pseudo-rapidity of negative 1.1 to 1. And its vertex is about 10 centimeters as well. And so with 3 years of data taking, we are hoping to have proton-proton, proton-gold, and gold-gold collisions. And we hope to have about just under 150 billion gold-gold collisions predicted for 3 years of running. So then to move on, just kind of go briefly through all the different subdetectors. So as I mentioned before, at S-Phoenix, we have currently 3 different trackers. We have a monolithic active pixel vertex detector, the MVTX. We have an intermediate silicon strip detector, and we have a compact time projection chamber as well. So to move on to the MVTX consists of 3 different layers of staves, and we have 50 micron monolithic active pixels, which we are using the Alpide sensors, which are used by the Elise detector. And also along with the Alpide sensors that we're using, we're also using the same readout units that Alice uses, but our back end that we have in the counting house is the Atlas Felix detector as well. So as I said, we have 3 active layers of sensors, which start at about 2.5 centimeters from the beam spot. And each of these staves that we have 9 of these Alpide sensors per stave, and this covers about 27 centimeters across. And on the bottom right, you can see some photographs of these staves as well. Now, a couple of important points that we have about these staves. I've already mentioned that they're 50 microns thick for the sensors, and including our cooling and support structure, we have about 0.3% of a radiation length for the material budget as well. These are quite low power consumption, so we're expecting to have about 40 milliwatts per square centimeter, and each sensor itself is about 3 by 1.5 centimeters as well. We are aiming to have a spatial resolution less than 6 microns, and we have a few test beam results that I can show as well after this. And our timing resolution, which is tunable based on the pixel parameters, is a few microseconds, which lines up with the S-Phoenix trigger latency that we have as well. So a few results that we have from a test beam that we took last year at Fermilab. So on the left, we have the spatial resolution as a function of the trigger delay that we have, and we have a uniform spatial resolution of less than 5 microns, which is better than what we wanted, across in our X and Z planes as well for all the tracks we took with using 4 staves last year. And similarly, for our timing resolution, we can look at the number of pixels that were fired per event, which can be likened to the efficiency of our detector. And we can also space this out by our trigger delay that we had. And as I said, the S-Phoenix trigger delay is on the order of about 4 microseconds. And you can see that we kind of have maximum efficiency that we can tune to well beyond this trigger latency as well. And last plot that I want to show is the 2-dimensional impact parameter resolution that we have using the MVTX. And you can see that our impact resolution is down to about 6 or 7 microns as well for high PT tracks. So one of the other trackers that we have is what we're calling our compact time projection chamber. So most TPCs are fairly large. However, the radius that we have between the electromagnetic calorimeters and the silicon strip detector that we have gives us a space between 20 and 78 centimeters to use. And we actually found that the active volume that we have is going to start at 30 centimeters as well. So that's why we're calling this compact. So we were aiming to have a spatial resolution of 200 microns. And on the bottom left, we had a TPC prototype taken to test beam as well without the magnetic field. And we measured the resolution, which is on the bottom left, the data points. And then we further extrapolated that out to what we'd expect with the Babor magnet of 1.5 Teslas. And we can see right up to our maximum drift length of a little bit over 1 meter, we can keep below this 200 micron resolution as well. So as in, we're using charge collection here from stacked gems, and this will be read out by the Alice Sampa chip as well. And with using these stacked gems, we can keep the ion backflow to a minimum. And we have measured this at several kilovolt to be below 0.5% as well. And we're also looking at the space charge effects and what we can do to measure and correct for this in our data taking as well. So moving away from trackers to our calorimetry. So one of the big aims for S-Phoenix is to measure jets in heavy ion collisions. So we have our 2 different calorimeters. We have electromagnetic and hadronic calorimeters. So the electromagnetic calorimeter is a sampling calorimeter where we have tungsten powder mixed with an epoxy, and we place scintillating fibers inside this as well. And on the top right, you can see kind of a stack up of 4 different towers that we're using as well at S-Phoenix that's been constructed. We have a very large radiation length and a very small interaction length, as you would hope. And you can also see the energy resolution as well that we are aiming for. So at test beam, we were able to measure this resolution, and you can see that at high energy above about 12-15 GeV, we drop below this 6% resolution as well. So this is a very, very large number of readout channels. You can say we've got about 25,000 of these different EM-Cal towers. We're using the Hamamatsu SIPMs as well for this readout. Now on the bottom left, you can see a drawing as well of what one of these EM-Cal sectors look like. And this would be effectively underneath the beam with the beam above it as well. So we have our calorimetry systems tapered, which allows us to point back into the center as well for better resolution. And then moving on to our hadron calorimeter. So this is another sampling calorimeter, and we have 2 different calorimeters outside and inside of the magnet. So our inner and outer HCal. The outer HCal uses layers of steel and scintillator, whereas the inner is using aluminum plates as well. And we have an interaction length of just under 4 as well here. And this extends out to the maximum distance of S-Phoenix. So currently this is down as being our final detector. This was also taken to test beam as well, where we were able to use different species to try and reconstruct the energy of the beams. You can see on the bottom right, we were using 16 and 24 GeV pion beams. We had this managed to match up quite well with our Géant 4 simulations. And on the right, you also have the resolution as well. And you can see that the pi plus and pi minus resolutions match up on top of each other. So then moving on to the current production status, I guess all of us have tried to adapt to our new world of COVID-19, working from home, reduce work at labs. So we've done a lot of work to try and work around about this as best as we can in as safe a way as we possibly can. So as I showed in one of my first slides, we have already, before everything shut down, cleared our experimental hall to start construction. As for the MVTX, last month our stage production was resumed at CERN, and we expect that to be completed by early next year. And currently all the readout units that we need have been delivered to the US for further validation and testing. The gems for the TPC have been ordered and should be expected to arrive this summer as well. And on top of what I've already shown, they are now looking at testing the cooling equipment they have for electronics as well. So to quickly build together both of the calorimetry systems, we've got most of our equipment has been delivered. Everything is expected to be delivered by the end of the summer as well. So I can say all the tungsten and SIPMs have been delivered, and the rate of tails and fibers is massively increasing as well. And we're hoping to have that finished in the next several weeks. So the photographs that we've got on the bottom, you can see the sample chips that we've got delivered for use in the TPC. And on the right, we are repurposing classrooms in different universities to store tails while we're doing our construction as well. So as the last topic I want to go on, so I've shown what S-Phoenix is, what status we're currently at. So I want to show what reach we also have. So the four main physics pillars that we're trying to aim for is looking at the jet structure. We want to look at heavy flavor physics from C and B physics, cold QCD, and one thing I want to touch on quickly here is quarkonia and upsilon spectroscopy as well. So this plot that we have for the upsilon spectroscopy is without background, but this is expected to show the yield that we would see in S-Phoenix, and this would then give us the very first distinction between the different resonance states for upsilon spectroscopy at RIC as well.
1 minute left.
Okay, right, that's fine. So then to go into kind of the physics potentials here, I was mentioning that we want to do heavy flavor physics and jets. So then to quickly show that we have for our C and B physics here, on the left, we have the reconstruction from the tracking of kaons and pions. But this is using an event reconstruction package that's been used in several other experiments, but just using our tracking, we have very good signal to background ratio and yield for D0 decays. And then for any B physicists that are in the audience as well, the middle and right plot shows the golden channel of B sub S to J psi phi that we have reconstructed. And the middle plot, this is without having any constraints on the J psi or the phi mass, but when we apply these constraints, we end up with a resolution below 20 MeV as well on this peak. So we're expecting that we can do some good sort of B hadron measurements here as well. And then my last slide before the conclusion, I want to quickly show that with the jet measurements that we're having, if we look at the corrected secondary vertex mass, we start to have distinctions between the B and C jets as well. Now looking at directed flow measurements in the middle, comparing with measurements that we have from STAR, with the S-Phoenix data set, we should have the statistics to be sensitive to any separations between the D and D0 from the initial magnetic field. And then the last thing is to show RAA measurements. And looking at an RAA measurement of non-prompt D decays, this looks like we could be theory limited here at the end from the S-Phoenix dataset. And as I think I have came to time, I will also not go over the conclusions, but I'll just say thank you for your attention.
Thank you for the nice and very complete talk. So are there questions to Cameron? Raise your hand if you want to ask. Let me check also the Mattermost channel. So it seems there aren't questions, but actually I have one. Could you go back of one slide about the performances? You mentioned here the direct flow. And what about elliptic flow? Would you be able to?
So I skipped the V2 measurements here. So I could probably maybe have a bigger discussion on this on the Mattermost channel, but we're, again, as expected with the direct flow, we'll be reducing the uncertainties here, but there's nothing really to say on the predictions there publicly just now.
Okay. Thank you. Any other comments or questions? If not, we thank Cameron again, and we move to our next speaker, who's Stefano Panebianco from Alice.
Yes, hello, can you hear me?
Hello, Stefano. Yes, we can.
Perfectly. Okay. Can you see my slides, I guess?
Yes, we do.
Perfect, thank you. So I'm going to present you the Alice detector upgrade for run 3. As you probably all know, the LHC schedule has been moved because of the COVID pandemic. And now our baseline scenario at CERN is to have the first beams in May 2022. This implies probably some quiet beams already at the end of the next year, but this is still to be confirmed. And then to officialize the end of LS2 by February 2022. So the idea is to have the first PP physics by mid-May, but the good and important news is also that all the heavy ions runs are kept because the present scenario implies a bit less than 20% PP physics days, but the heavy ion physics has been kept unchanged up to now. Is important also to take note the fact that Alice is continuing taking data as usual also during the PP run at 13 TeV. So you can see here our expected luminosities. So what we expect is to have 5 inverse nanobars in LED at 0.5 Tesla, and then also to have a bit less than half of this luminosity at a reduced field, which is very important for us. And then to have PP reference data at 5 and 8 TeV correspond to respectively 6 and 3 inverse picobars. And hopefully also some asymmetric collision with the proton LED system. So to take benefit of this nice new beams that we are going to have starting from 2022, Alice has done a major upgrade to cope with increased luminosity and to improve its vertexing, in particular and tracking, in particular at low PT. So these are the different projects I'm not going to talk about because you will have a very nice talk, for example, about the new fast interaction trigger that will be presented just after me and on the 2 poster in the poster session. And then you will have even 3 dedicated talks on Thursday about our new framework of online, offline computing, which we call O². What I'm going to concentrate on in this talk are essentially 3 upgrades. The first one is the TPC, the second one is the MFT, and the ITS. So the inner tracking system, the muon forward tracker, and our big TPC. So this will allow us to really open a new physics channel and to improve, in particular, our systematics in our core physics, I would say, in particular, charmonium state, the study of dileptons, in particular in the low mass region, and also the study of light and hypernuclei. So let's start now with the TPC. As you know, we have the biggest TPC with a diameter of 5 meters, 5-meter length. Let's say, present limitation of this detector is its ion backflow. This is a very known limitation for this detector. It's composed by 18 sectors on each side. You can see here in the picture what we call the inner sector, the EIROC, and the outer one that we call OROC. Up to now, during run 1 and 2, we have been using the wire getting grid technique to collect the ion backflow, but this limits the trigger rate up to, let's say, a few kilohertz. And what we're aiming is 1 megahertz PP and 200 kilohertz LED. So in order to reduce this ion backflow, considering the increased luminosity in the LHC, the current upgrade the current upgrade makes use of what we call the GEM, gas electron multipliers, which are MPGD, who avoid this gating grid and allow continuous readout up to 50 kilohertz. You can see a sketch of, indeed, it's not a simple GEM, but a stack of multiple GEM detector, which constitutes the readout chambers of the upgraded TPC. You can see here the status of the this upgrade. First of all, we had to extract this big detector from the cavern and then transport it to a clean area where the readout chamber installation could take place. You can see here also a nice picture of a view inside the TPC. And now you can see here the picture taken just a few weeks ago with a fully instrumented upgraded TPC, because now all the readout chambers have been installed together with the front-end electronics, and the tests are going on surface, and they are under finalization, because already next month this detector will move to the cavern for a long sequence of installation that will take up to the end of the year. Then some results from this pre-commissioning on surface. You can see here nice calibration data taken with the laser tracks in the TVC. You can see here this nice track. The excellent noise figure that we obtained. This is an example of one readout chamber with a noise figure of 1 ADC. You can see also already the first cosmic data, the first cosmic track crossing our detector. This was a very exciting result for us. This commission is ongoing, as I said, and is going to finish in the coming weeks. Then the second major upgrade of our detector is in the central region. You can see here our current beam pad that will be completely replaced together with the inner tracking system, which has different layers close and then farther from the beam, together with an end cap, a forward detector for detection of muon, together with the fast interaction trigger. So let me describe these detectors, starting from the ITS, so this inner tracking system, which is there essentially to reduce at minimum the material budget, to improve the tracking performance, especially at low PT, which is the interesting kinematic region for ALICE. It's a very large detector with an area of 10 square meter, made of monolithic active silicon pixel detector, covering episode repeated range between 1.22 and minus 1.22. Is made of 7 layers, from very close to the beam, from 22 millimeters up to 400 millimeters, and is arranged in the inner, middle, and outer barrel, aiming at a spatial resolution of the order of 5 microns. And the first layer, and this is a main modification with respect to the old ITS, is the first layer is very close to the interaction point, thanks to the small beam pipe radius. And we aim at 0.3 x0 per layer for the 3 innermost layers of the detector. It has a structure made of staves. You can see here with a very light carbon fiber structure. These staves are made essentially of flexible circuit where we interconnect our sensor, our silicon sensor. Same technology is used by this end cap, which is a completely new detector, which is called MFT, muon forward tracker, who is devoted to the detection of muons to add vertexing capabilities to the present muon tracking, which is on the forward region after a hadron absorber, is made of a bit less than 1,000 silicon pixel detector, same type of the one used for the ITS, 0.5 square meters, arranged in disks. You can see here 10 half disks with the 2 detection plane each at a different distance, very close to the interaction point. The common tool for these 2 detectors is what we call the Alpide pixel sensor, which is, as I was saying, a CMOS active sensor made on the 0.18 micrometers tower jet technology. This has been thinned down to 50 micrometers for the MFT and the inner layers of the ITS, and to 100 microns for the outer layers of the ITS. We have, so it's a very dense detector with more than 100,000 pixels per centimeter square, with a very high detection efficiency, and as I was saying, a spatial resolution of 5 microns, capable to stand a very high radiation dose. You see here the figure of the cumulative run 2, run 3, run 4 expected radiation dose. For more details on this sensor, I really invite you to have a look to the poster of my colleague Kushpil. And then now let's come to the status of these two detectors. First of all, the ITS status. So you see here a nice picture of the inner barrel and here of the outer barrel. So this part of the detector is already fully assembled, is actually under test on surface, as it is the case for the TPC. You can see here already some very nice results. For example, already muon tracks coming from 1 week of shift operation. And you can see here very nice picture of the fake it rate, which goes down to specs, so 10 to the minus 11, few tens to the minus 11, just by masking few pixel in the markets, which shows a very, very nice low noise performance. On the other side, the MFT, again, here the detector is fully built. So here the assembly is a bit different because the integrated circuit are glued on these discs. You can see here a picture of a complete disc, and then these discs are mounted on a cone. You can see here a fully mounted cone. You can see here also a figure of the threshold of the homogeneity of the threshold over a full disc, very homogeneous and low noise. So these detectors, as I said, is already fully assembled and again under test on surface. Its installation together with the ITS is scheduled by the end of this year, beginning of next year. Now let me finish with then the installation sequence that we are expecting starting from already next month. As I was saying, the installation of the TPC in the cavern, then in September, the installation of the new beam pipe and the ITS cage, then the installation of all the services which are housed in what we call the mini frame, then end of the year and beginning of next year, installation on the MFT, followed by installation of the ITS, then let's say the end cap on the other side, which is the fit A, so the fit detector on the A side, and then the start of the global commission, which is expected to start next year in September, in order to have 4 full months of global commissioning up to the end of LS2 in February 22. So in conclusion, we have a very nice major upgrade for the ALICE detector, which will allow us to take a factor of 10 increase in LED integrated luminosity. This major upgrade is essentially in its end. We have now the detector, which is essentially constructed. The construction is completed, in particular for the 3 major ones, so the TPC, the ITS, and the MFT. The installation sequence will start next month, but this is not the end of the story, because we are already working very hard on the new upgrade for the in view of Run 4, and for that I will invite you to see, if you have not seen it already, the presentation of Andrea Rossi that took place today just before me. And thank you very much for your attention.
Thank you, Stefano, for the nice presentation. So are there questions to Stefano? So I don't see any raised hand. So, well, Stefano, could you give us some hints of the physics performance of the upgraded apparatus?
Thank you, Stefano. I was a bit frustrated by the time, and I had to put away some nice performances plot that I have put in my backup slides. Is because I think it's nice to show that the tracking performances or in the central barrel, thanks to this new ITS and the coupling with the TPC, will allow in particular to improve drastically the tracking efficiency, especially at low PT. You can see here the improvement at low PT, and together with this drastic tracking efficiency improvement, we will also drastically reduce by essentially more the factor of 3 the pointing resolution, again, especially at low PT, which is really the important region for ALICE. And this is done always keeping the PID performances of the TPC and ITS combined unchanged, which is also a major achievement for the experiment. And this is true for the central region, but is also true for the forward region, where this is not an improvement, but these are really new performances, because this is a new detector, and it will be the first time that we can finally get a pointing resolution for muons in the forward region. You can see here already at low PT will be around 60-70 microns, and this will go down to 30 microns at high PT. So this is a really good performance that will open new physics channel, and for the core physics improve our systematic uncertainties on the main measurements.
Okay, thank you, Stefano, for these other plots you showed us. And let's move to the next ALICE presentation about the fast interaction trigger by Maciej Slupecki. Okay, we see your slides.
Okay, excellent.
Okay.
So, yes, hello everyone. Let's continue with the ALICE upgrade. I would like to introduce you to the fast interaction trigger, which is located around the beam pipe in these 4 regions of ALICE. It's quite spread, as you can see. And first of all, I would like to start from asking a question: why ALICE actually needs the fast interaction trigger, because it has moved to the continuous readout for the majority of the detectors. But nevertheless, some of the detectors still use the triggered readout, and for that we need the fast interaction trigger, which features the online vertex determination. And it has the capability to select the minimum bias events and also centrality-based selection. Then it will reject beam gas events and veto and provide veto for the ultra-peripheral collisions. Another online function of the FIT is the luminosity monitoring with the direct feedback to the LHC, and this is essential for beam tuning and all the servicing regarding the beam quality at that point 2 where ALICE is located. From the physics point of view, FIT will provide forward multiplicity from which the centrality and event plane can be reconstructed. And then it will participate in particle identification by helping the time of flight detector with collision time. And it will also participate in diffractive physics. So a bit closer look to the FIT detectors or subcomponents is shown here. So on the outer edges, you can see the 2 FDD arrays, which are just short of 20 meters away from the interaction point. Which is at the very center here. And then you can see the 2 arrays of FT0, A and C, and then FV0 ring, which is adjacent to FT0A. Now, all of these 3 subsystems are, in a sense, unique and quite different. FT0 is composed of 2 Cherenkov arrays with quartz radiators. And it specializes in low latency and in background rejection. So it is capable of generating minimum bias trigger and measuring cleanly luminosity. It also has an excellent time resolution of 20 picoseconds or better. On the other hand, FV0 is a scintillator. It has 5 rings and 8 sectors. It also features low latency. And the time resolution is 250 picoseconds, which is very good considering this is a, let's say, 1.5 meters diameter detector. So for such a large detector and using scintillation technology, this is a good result. Because it's scintillator, it can monitor background, and because of the large area, it specializes in multiplicity trigger. Then FDD is located at the very forward rapidity. It's also a scintillator. And thanks to the forward rapidity location, it gives us access to the diffractive physics and background monitoring. So for all of these three subsystems, we have decided to use the common front-end electronics, which has been custom designed, especially for that. And it will be capable of reading out the data from the sustained PP operation at 25 nanoseconds bunch crossing at a high dynamic range. So each of the channels is capable of detecting up to a few hundreds of charged particles. Then all the detector has to be radiation hard because it's located close to the beam pipe, and therefore there is no active electronics at the detector. All of the electronics is moved outside quite some distance away, and therefore FIT will survive run 3 and 4 without major component replacements. Now, if we go with the subdetectors one by one, FT0 is a Cherenkov detector, as I already explained. At the heart of each detector module is an MCP PMT photosensor, which has been modified especially for FIT. And there are 4 quartz radiators and 4 readout channels for each of these detector modules. Then there are 2 arrays, FT0C and A, which have 28 and 24 modules. And then FT0C has a concave shape because it's closer to the interaction point, and FT0A has a planar shape, it's further away. Then FV0 consists of 48 readout channels and 40 scintillator cells. The difference here comes from the fact that there are 2 channels for every 5th ring cell. And one special thing about FV0 is its novel collection system. We had to do something to keep the pulse width below 25 nanoseconds. And this meant getting rid of wavelength shifting fibers. And therefore, as you can see on the bottom right drawing, the clear fibers are attached perpendicularly to the white colored scintillator on this picture. And then FDD, which is the acronym for Forward Diffractive Detector. This consists of 2 arrays of 2 layered scintillators, in total 16 readout channels. This detector uses the wavelength shifting bars, but it has applied the very novel NOL 38 wavelength shifter, which is fast. So that's also important. And more information about it you can find from the poster by Solanhel. Now about the electronics. The basic building block of our electronics is this processing module, PM, which consists of constant fraction discriminators, analog to digital converters, and charge integrators. And there are 12 channels in each of them. And these modules connect to a trigger and clock module, which gets pre-trigger solution from the processing module and generates from many processing modules and generates final triggers. Since the travel restrictions, we have been focusing on electronics development. So here are the latest results. We have achieved the vertex trigger resolution at the most challenging low channel multiplicity and at low pulse amplitude per active channel of the order of 20 picoseconds. For ALICE, the requirement is 50 picoseconds, so we are well in line with that. Then if we look at the test of the final electronics in terms of charge distributions, this middle plot shows 4 random channels from our latest 12-channel prototype. You can see they are nicely aligned with the baseline and the mean values aligned. And on the right-hand side, there is a correlation plot between charge and time, which shows no correlation, and therefore we can infer from there that the constant fraction discriminator works correctly. Now, as for the physics performance, one of the figures is the event plane resolution. And for that, I invite you to see the poster of Heidi on Friday. Now about the status of all of these systems. So I will go system by system. FT0C is completely finalized. It has been assembled, integrated within the common structure with MFT, and all connections are tested by now, and this is ready for the installation together with MFT. Then FT0A, this is the components for assembly are ready and tested. However, currently this final detector is used for front-end electronic tests. So it's away from CERN currently, but after transportation, we need to do simple modification of metal structure, and the expected assembly is relatively fast. It would take 2 weeks or less than 2 weeks to assemble the whole detector. Then testing is not long either, 1 to 2 weeks, so this is fine. Then FV0 is almost assembled. The only measurements to be completed are the pulse shape verification of each channel. Then we need to adjust the front-end electronics for the FV0 needs because it was designed for FT0 and all the other detectors use the same, but front-end needs to be a little bit tuned. And then we need, for reference, we need to measure a charge of cosmic muons. Then the FDD arrays are not that advanced at the moment, but the characterization of photosensors is almost completed by now. And the assembly of the detector is rather fast. In total, it's below 1 month. As for the electronics, this is a bit more complicated to explain because the components have been tested in parallel with assembly and with the final standalone testing, because we need the green light to start the mass production only after the tests are completed, which is coming within 3 months estimated. So here I present the final, or not the final, but the present schedule of installation at ALICE of these components. And I have highlighted only the FDDC, which is 3 months from now. And there we may have a problem. However, we still have a secondary slot for installation at the beginning of 2021. So if this fails, we still have a backup solution to install that. Otherwise, all the other detectors are either ready or well in a good shape for this timeline. So to sum up, the FIT consists of 3 very different subdetectors, and despite that they use the same or very similar electronics. These detectors are in the middle of assembly phase and testing. And in terms of hardware, the main focus has been on electronics recently, and the FIT assembly and testing is basically on time for installation. Thank you.
Thank you for this nice summary of the production of this complex detector. Are there questions? Let me check. Let me check also the Mattermost. Okay, so I don't see any question, but I would like to ask you about the qualification tests you mentioned during your presentation about tests on photodetectors. You have many different components. Could you tell us about results in this pre-assembly phases?
Yes, for example, for FT0, we have done the very extensive tests, which took 1.5 years for 60 sensors. Because this has to be very reliable. We have no access to the seaside detector basically for the next 3 years. So they need to be extremely reliable and properly checked. So one of the basic tests that we have done was the gain scan. You can see an example here. With these photosensors, we are planning to run at a rather low gain of 15,000 only, and this is achieved at 1.2 or 1.3 kilovolts, depending on the sensor, but we need to know that simply. Also, one important test was the long-term high voltage stress test, because we have noticed these sensors, while they are very robust, generally in the initial phase, when you just receive them from the manufacturer, they sometimes show a breakdown. So in here you can see the current trends of three examples of the sensors. The black one is perfectly fine. The red one had a problem, and then after conditioning, running it at high voltage for quite high voltage for a longer time, something has discharged inside, and then it fixed itself. And we know from experience that after that, it works in a stable way. However, the blue one, as you can see, is bad and is expected to continue to be bad. So we had to reject this sensor. So this was one of the most important and also time-consuming tests, because we had to test the sensors for at least 3-4 weeks to reject the bad ones and to condition all of the sensors. One more thing is the operation within magnetic field. You can see the following publications here for details about that, because this was another extensive measurement for all of the sensors.
Okay, thank you once more for clarifying this. Any other questions? So if not, we thank you again and move to the next presentation, which is now about LHCb detector performance in Run 2 by Martina Pili.
Yes, hi. Can you see my slides and hear me well?
Yes, we do.
Okay, great. Yes. So yeah, it's a pleasure to give this overview of the performance of the LHCb detector during the Run 2. So let's start with a brief introduction. So LHCb is a single-arm spectrometer developed at forward pseudorapidities with main focus of studying CP violating processes and rare decays of beauty and charm hadrons. However, over the years, the LHCb physics program extended to wider topics. The heavy ion program, the electroweak and exotica physics are just a few examples. But the focus of today's talk will be really an overview of the excellent results achieved in performance in terms of tracking, alignment, and particle identification during the Run 2, so covering the years of data taking from 2015 to 2018. So I want to stress out really the importance of having a good detector alignment and calibration in the LHCb physics program. To give some examples, the first two plots are showing, so on the top are showing the improvement in the, let's say, the epsilon mass resolution in a sample of epsilon to mu decays after the application of a better alignment. On the other hand, most analyses rely on PID requirements, particle identification requirements, that relies on good calibration of the relevant subdetectors. And on the lower plots are showing especially the right-hand side plot is showing the improvement in selecting or the impact of applying PID requirements to select the signal of interest, these B to pi decay, suppressing the favored K-pi mode and combinatorial backgrounds. So all these aspects are crucial to achieve the excellent performance in the LHCb physics program, and they need to be under control. So the excellent performance that we achieved in the Run 2 were made possible thanks to a novel real-time analysis strategy that was introduced in 2015. LHCb is the first detector to have a full real-time detector alignment and calibration performed in the trigger farm, with full event reconstruction available at the second stage of our software trigger, what we call HLT2, and with the quality of these online reconstruction matching the offline reconstruction. And this has huge consequences in terms of the performance, because first of all, it allows for some analysis to run directly from the output of the trigger, and this is why really the set of the set of trigger lines grouped in the so-called turbo stream was developed for. but it also allows the selection of high purity and high statistics calibration samples that we use to measure our tracking and PID performances, and using some dedicated trigger lines grouped in what we call TurboCalib stream. And this is what we're going to discuss today more extensively. So let's start with the tracking. The sub-detectors that made the tracking system are the vertex locator that provides high precision measurement of the position of primary and secondary vertices, the dipole magnet together with the upstream and downstream tracking stations that provide measurement of the track momenta with excellent momentum resolution, and then 5 muon stations that contribute in reaching really excellent reconstruction efficiencies. The alignment is that again takes place in the trigger farm, consists in the minimizations of the residuals of a Kalman filter fit, where multiple scattering and energy loss effects are taken into account. The sample that is used for the alignment consists into a minimum bias sample for the velo and a D0 two-body decay for the tracker. But it's important to mention that in 2017, an additional alignment was developed using offline, using 2016 Z2MU data. And this is important because, of course, high-PT tracks are very suitable for alignment studies as they are very sensitive to very small misalignment effects. So the plot on the right-hand side is really showing the impact in the Z mask resolution, the impact of applying the Z alignment on the Z mask resolution. We're talking about an improvement of 35%. And so in 2018, the Z alignment was used as a starting point of the real-time alignment. These improves a lot the quality for high PT tracks without affecting the already excellent performances at a lower PT. But this is something that we introduced during the run too. So it's a recent progress. Then in terms of the actual performance measurements, so in tracking efficiencies, these are estimated using a data-driven approach, using a tag and probe method, where you can see in the plot here in the scheme, the tag is fully reconstructed, where the probe is reconstructed using only hits in some subdetectors and excluding the subdetectors that want to be hits in the subdetectors that want to be tested. The sample used for the tag probe method is a sample of J-side to mu decays because of the clear signature left in the detector and the high statistics available. And this sample is selected using dedicated trigger lines in the TurboCalib stream that we mentioned at the beginning. So it's important here to mention that most analyses really rely on actually calculating, in order to mitigate for data and simulation discrepancies, most analyses rely on calculating ratios of efficiencies between data and simulation, as this cancels out first order systematic uncertainties. And there is a dedicated tool available for all LATB users called TrackCalib that provides these ratios of efficiencies, and it's very simple to use and very immediately available for all LATB analysis. So there was a lot of work that was performed over the years to provide these tools in the most immediate way. Yes, so in terms of actual performance measurements, these are the muonic tracking efficiencies for 2018 data and simulation, investigated different variable dependencies. We can see that the muonic efficiencies are well above 95%, with a very good agreement between data and simulation around the 99%. And this pattern is also stable over the years, as we can see comparing years of 2012, 2015, and 2018 of data taking. Here it's important to mention that we have a mention of honor for the electrons. So we have a dedicated strategy to calculate electron reconstruction efficiencies, which was developed in the last years. So electrons tend to behave differently than muons because of the high amount of energy loss due to Bremsstrahlung in the material. These affects mostly the reconstruction after the magnet. And so a dedicated tool, so a dedicated strategy was developed. So it consists into a tag and probe method using B to J psi K decays, with the J psi decaying into 2 electrons, and where really the tag here in the tag and probe method is represented by the electron plus K-on pair, where the spare electron is representing the probe. So more details are in the backup slides, but also in the recently published paper. But yes, over the years we had also improvements in the treatment of the electrons. Then the second part of the talk is dedicated to particle identification. So the PID systems at LHCb consist into 2 ring imaging Cherenkov detectors providing particle identification information for kaons, protons, and pions, covering now the 2 reach covers a wide complementary momentum range. Then we have calorimeters providing PID for electrons, photons, and neutral pions. And finally, again, the muon system that contributes in reaching, that provides high purity PID for muons with very low mis-ID rates. Now, the informations that we have available for PID are different for charge and neutral PID. For charge PID, we can combine the PID informations from for all the relevant subdetectors into single powerful observables. One is what we call DLL, is defined as the log likelihood difference between a certain PID hypothesis and the hypothesis of that track being a pion. We can also train multivariate classifiers to obtain what we call provenance X, using also the information from the tracking system. And this can be interpreted as really the probability for a given PID hypothesis. And then instead for neutral PID, we have dedicated neural nets to separate photons from other species. We see more details in a couple of slides. Now, it's important when we talk about really PID performances to mention that so since the PID response is not perfectly described in the simulation, using a Monte Carlo to calculate PID efficiencies would introduce large systematic uncertainties in the measurement. So what we do is to calculate these efficiencies from data-driven techniques using dedicated calibration samples that are selected using specific HLT2 lines in the dedicated TurboCalib stream, using a very similar procedure to what we used for the tracking calibration samples. So these samples are characterized by being high purity and high statistics samples with low track multiplicity and large branching fractions. As you can see from the table, for different particle species, we have different samples covering different momentum ranges. And so this is just for the charge. We'll see in a moment for the neutral particles. Now, some very new results for PID, charge PID performance in the year 2018. Here we have we're showing the kaons and protons identification efficiencies in red compared to the pion mis-ID rates for different cuts on the DLL and provenance variables that we described in the previous slide. So here you can see that there are two. We evaluate we show 2 different possible cuts on the DLL and provenance variables. One cut is looser, and this guarantees higher signal efficiency, and the tighter cut instead is characterized by having a yields to higher background rejection. But we can see really that there is a very good particle discrimination, PID discrimination over a quite wide momentum range. So that is good. And these patterns are also stable over the years, as we can see, comparing all the 4 years of the run of the data taken in run 2 for both provenance and DLL variables. And except there is just one we can there are just some very small differences from 2017 onwards due to some known changes in the tracking performance, but overall you can see that the results are stable over the years. Then final mention for neutral PID performance. We said we have 3 dedicated neural nets trained on the simulation to separate photons from electrons, hadrons, and neutral pions. And then the output variables from these training are the is not E, is not H, and is photon. The lower plots are showing the results from this training to say that show a good separation between photons and the backgrounds represented on the left-hand side by electrons and on the right-hand side by non-electromagnetic particles. Now there is a work ongoing to provide data-driven tools to provide really the neutral PID efficiencies. We can say for now that the same production strategy that was used for the production of the charge PID calibration samples was extended in 2017, sorry, to neutral calibration samples, and covering also a wider phase-space coverage with respect to what was available in run one. So yes, there is a work ongoing also to provide these tools for neutral PID. So just to conclude, really, I hope to have shown you that precise alignment and detector alignment and calibration and particle identification are crucial elements of the LHCb physics program. LHCb, we could count on a novel computing strategy during the run two that made the LHCb the first experiment with real-time alignment and calibration of the full detector with the full online reconstruction with quality matching, with online reconstruction matching the quality of the offline reconstruction. And this novel computing strategy allowed the selection of the high statistics and high purity calibration samples for our performance measurements. So in terms of the actual performance, the muonic tracking efficiencies are well above 95%, and we developed dedicated strategy to treat the electrons. And in terms of PID, we showed excellent performances stable over the entire run two. So all these aspects are really the starting point and the basis for what is going to be the run three. And if you want to know more, I just invite you to stay tuned for the upcoming talks. Thanks.
Thank you, Martina. Really impressive results from LHCb. So I do see, yes, Tadeusz, you have a question. Go ahead.
Yes, my question is, what was the main improvement or change in the alignment? Was it the introduction of the mass constraint?
No, actually, so the main improvement, yes, we use an alignment using this was all developed offline, but yes, the idea was that to have an alignment with a mass constraint applied to the Z candidates, and the idea is that the track quality for high PT tracks were improved, whereas while the quality for lower, like the performances at lower PT stayed invariant. So it's a real improvement it's seen in analysis that involve high PT tracks, especially like the ElectroWeek program took a lot of advantage from yes, these the improvement, the introduction of the Z alignment.
Okay, thank you. And if I might, so you do this kind of complete alignment offline, and then based on that, you continue aligning some larger structures in the real-time procedure, right?
So what happens is, so the Z alignment was developed offline, and when we included it in the real-time alignment, which the alignment constants were used as a starting point from the real-time alignment. Where what we can do is to rerun the Z alignment offline, refit our tracks with the new alignment, and see really the improvement in let's say, yes, in these high PT tracks.
Okay, thank you.
Okay.
Yes, thank you.
Okay, thank you once more. Let's move to the next talk, still from LHCb. So the program for the upgrade for run 3 and 4 by Federico Alessio.
Yes, hello.
Federico.
Yeah, good evening, everybody. Can you hear me all right?
Yes, go ahead.
So now we'll talk to you about the plans for the upgrade for run 3 and run 4. You've heard from the previous talk about the excellent performance of the LACB detector. So this is the outline of my talk. I will just briefly mention the LACB at the LAC and the motivation for upgrading the detector, and briefly the upgrade plans for LAC round 3 and round 4. So LACB proved itself to be the forward general purpose detector at the LAC. It's well complementing the general purpose detector ASAS and CMS in terms of coverage and cellular rapidity. And as you heard from before, the physics problem from the LACB experiment was mostly dedicated to the beauty and charm sectors, but thanks to the excellent performance during round 1 and round 2, we also extended the physics problem to QCD, LA2 weak and direct searches. And in fact, we also participated as well in the heavy ion rounds, actively participating, which we will continue to do also in round 3 and round 4. So you heard the good performance from the previous talk. Now the question is, why do we want to upgrade? So we're going to upgrade now in this long shutdown that is happening now. The main motivation behind it is to go beyond flavor physics. So from moving from exploration studies to precision studies. You've heard surely that there are results from LACB, in particular in RD star, RK star, and angular analysis, for example. There are anomalies that have been observed, but no significant signs of mutation have been observed. And for this, we need to have more precision. More precision means, in fact, having more luminosity, which means that in practice, we need to run at a higher instantaneous luminosity. You can see here on the right-hand side of this slide, there is at the bottom, there is the luminosity, instantaneous luminosity, at which we were designed to run. We already run twice as much for the entirety of run 2, but this provoked some constraints, in particularly from the level 0 hardware trigger. There is, in fact, if you can see here, there is almost a factor 2 of trigger yield between the dimuon and the fully hadronic decays. In addition, if you want to increase the luminosity, we will have more data, which means that we have to fit within the bandwidth. So we needed to add the Usher cut on the PT and the AP. In addition, also, increasing the luminosity, we increase the complexity of the track record structure. So if you want to aim for more precision and higher luminosity, then we have to upgrade the detector. And for more precision and more precision, it means that by the end of round 3, round 3 and round 4, we expect to collect around 50 inverse femtobar. And you can see here in the table, in the column LACB 2025, what are the reach that LACB could achieve. And you can see that in gamma null mode, there is in the order of 1 degree, and for the ratio, the branch ratio of the BCBS, there is also around 30%. So the plan to do that is to do it now. So we are actually in the middle of the upgrade right now. The idea is to be ready by the beginning of round 3, such that by the end of round 4, we have collected at least 15 inverse femtobar. This is around a decade of data taking, which is added to the already decade of data taking that we have done, in which we collected in the order of 9 inverse femtobar. So the strategy for this is to remove the hard trigger, simply put, and to do the entire software trigger in software and read out an entire detector at the collision rate of around the elastic collision rate of 30 megahertz. Replacing all the detectors, in particular the tracking detector, the particle ID detector, and the beta detector to be able to run at a luminosity of 2 times 10 to the 33, and consolidate later on in the LS3, particle ID, the tracking, and the calorie method. There is also the plan to have a second upgrade, which is called LACB phase 2 upgrade, which is to happen for round 5 and round 6, in which the idea will be to reach in the order of 300 inverse femtobar, so to increase even more the integrated luminosity and to increase even more the instantaneous luminosity. And the only way to do that will be to include timing. I will not talk about this now, but this is just a flash that we have this in the plan. So the challenge is, in fact, to remove the level 0 trigger. Removing the level 0 trigger means that we have to record all bunch crossing, and all events have to be passed to the software trigger. The idea is, of course, that even if we take more data and we run at a higher luminosity, we want to maintain the same reconstruction performance in our shared environment. So you can see here the two trigger diagram from the left to the right. The left one is the one for run 2, and the right is the one which we are going to do in the upgrade. Practically, what we're going to do is just simply to remove the level 0 trigger. Now, how do we do that? Well, we have to develop a triggerless readout system. This is a system that has been developed over the past, specified and developed over the past decade. Ideally, we are going to put all the backend electronics in the surface in a data center, as you can see on the top right. This is connected to the detector front-end electronics by about 19,000 long distance optical fibers. In the data center, we will have a common backend board, which functions as a readout card, as a time distribution card, as a control card. The only difference is the firmware that changes the flavor of the card. And of course, you use modern technology to sustain this high rate, which is supposed to be a total bandwidth of 32 terabits per second. The events are then passed to the real-time alignment system, which was nicely introduced in the previous talk, so I'm not going to spend too much time, but the idea would be to perform the entire HEC1 in GPUs, the entire offline reconstruction in HEC2, perform the real-time calibration alignment as was described before, and maintain what we call the turbo model for exit selection in such a way that the data will be already available for physics analysis right off data taking. So what does it mean to have the full HEC1 in GPU? That, well, this means to include the full HEC1, which is the partial, the fast reconstruction, and the selection, which in LSTB is called Allen, the HEC1 trigger, into the event builder server. The events are then recorded by the detector, shipped over to the event builder server, which has a readout card. The events are then shipped around the event builder network, and then they come back to the server to be processed by the GPU. The GPU, the HEC1 has to run at visible collision rates of 30 megahertz, which means that over the order of about 500 GPU, this has to be 60 kilohertz per GPU. There is already about 3 candidates in the market that are available, and just as of today, so we are confident that there will be more candidates, GPUs available in the future. You can see on the bottom left a picture of the event builder server, which will contain the readout cards, which are called PCI 40, the GPUs, and the network connection. In terms of detector, how do we sustain this? Well, we need to replace the majority of the detector because we need to run at higher luminosity, but also we need to replace the entirety of the front-end electronics. In a snapshot here, there is all the parts that have been upgraded from the LACD. So in fact, one can actually say that maybe it's not just an upgrade, but it's in fact a new detector altogether. We are only keeping a very small part of the old detector, but the entire readout electronics and the DAQ system is going to be replaced. Only the calorimeter and the muon will remain as detector, as the one that were in run 2, but the electronics will be replaced. Now I will quickly go through the detector technology for this upgrade. More details are in the talk that are indicated in the slide. The first one is the vertical detector, which is the Velo. This is composed of 2 movable halves that they move to get closer to the beam while we are in collision. It's composed of 52 modules for a total of 41 million pixels. Detector technology is the hybrid pixel silicon detector modules, which are cooled down with microchannel at a temperature of less than 20 degrees. And for this one, of course, a new front-end chip has been developed, the ASIC Velo Pixel, which has the full detector ships around 3 terabits per second. A new tracking system has already been developed. This is composed of mainly 2 parts, one which is in front of the magnet, which is the upstream tracker. This is the detector technology for this is the silicon microstrip detector. It has, as it goes closer to the beam, there is finer granularity in different types of sensors. This is also cooled with biphase CO2 with a pipe integrated in the stave. And as well for this detector, there was also a new readout ASIC that was developed to perform pedestal homomorphic suppression and run at 40 megahertz. The second part of the tracking system is the scintillating fibers, which is behind the magnet. It is composed of scintillating thin fibers, which are, as you can see, 2.5, 2.5, 2.4 meter long, divided in 2 parts. It's composed of 12 layers of different layouts. The readout is done with silicon PM at -40 degrees. And as well here, there was also an ASIC developed for the front-end electronics. What this addition has, this detector, since it's a little bit further away from the interaction point because it's behind the magnet, it has also PGA on the front-end cluster board, which already performs clusterization and possibly dual suppression in case, also dual suppression in case this is the particulate is also being upgraded. This is the rich detector, imaging Cherenkov detector. This is rich 1 and rich 2, before and after the magnet. The HPDs has been replaced with the MAPMTs, a new readout ASIC, and as well, this one is also equipped with FPGA in the front-end boards for serialization and latching of the signal on the time. As I mentioned, for the calorimeter and the MUOD, the detector will not be replaced. There will be some small changes. In particular, for the calorimeter, the PMT will be reduced by a factor of 5 to support the increase in luminosity. And for the muon, there is an R&D ongoing which aims at replacing the inner part of M2, which is the part which is the module close to the IP, with multi-wire proportional chamber for higher granularity and better efficiency. What is different from the previous run is that both the calorimeter and the muon, we removed the detector which were used for the trigger, the level 0 trigger, since we don't have the level 0 trigger anymore. Last point that we are also going to upgrade is this smoke system. I will spend 1 minute on this system because it's a unique program at the LEC and particularly in LACB. This is the so-called fixed target physics. The idea is to inject a gas, a familiar gas, a species of gas. As you can see on the bottom left, these are the gas that we have injected in run 2, in both in PP collision and in ion during the ion run. The idea is to inject a little bit of gas into the very close to the IP, basically inside the velo, and look for this P-gas interaction. The smoke system, this is how it was called, is being upgraded with a new gas cell which is attached to the velo, and has a displaced proton gas IP, which allow us to perform the reconstruction of this type of data, proton gas or ion gas, with the in parallel to the PP data. This is of course allow us to expand even more the physics program, in particular to anti-proton production, CEP, central express production, strangeness, various ratios, etc. This is not to forget also that LACB will participate as well in the heavy ion runs, both in the PP, in the ion data taking, and also in the PPB and the ion proton data taking. This is because with the new detector, we are able to go down to about 30% centrality in run 3, which is a big step from the previous study in run 2. In terms of installation and commission, it's clear that also LACB suffered quite a bit from the COVID pandemic. We are still aiming at having the cavern fully closed. We are having the cavern fully closed by November 2021, in time for to conclude also the global commissioning. And the plan, of course, has been adapted as well for being able to restart the full speed installation in autumn 2020. So to conclude, the LACB experiment has successfully taken data already during run 1 and run 2, and the physics problem has been extended beyond the original design program. We are currently preparing for this upgrade in run 3 and run 4. The idea is to collect at least 50 inverse femtobarn by the end of run 4. The idea is to maintain the same level of performance that we had in run 1 and run 2, but a higher luminosity, and so collecting more data. We have developed a new completely readout system with common electronic and a very high throughput, a full software trigger, which is on model GPUs, and new detectors with new technology to support a higher integrated luminosity. As well, LACB has extended also its physics program to the fixed target physics program, and also our participation in the ABI. So I invite you to stay tuned for more news from the LACB detector. Thank you for your attention.
Thank you, Federico. Again, an impressive list of changes you're planning to upgrade your setup. So I don't know if there are any specific questions from the audience. If not, I would start asking, according to you, which is the most challenging or critical aspect of this upgrade?
Well, this is the most challenging factor, the fact that this is a completely new detector, in fact. So we will have to basically redo everything that we have done from run 1 and run 2 and restart. We had the upgrade was quite challenging per se, because we wanted to do the upgrade a little bit asynchronously with respect to the high Lumi LAC upgrade. So we wanted to do it one shutdown earlier, which at the time was a bit tighter. Then, of course, we had unfortunately the pandemic, which has slowed down a little bit, but the schedule from the LAC has been adapted accordingly as well. So we are very, very happy about it, and we will profit to try to make all the detector work just as much as before. But I think that all the aspects, including also the triggerless readout system and a full trigger system and GPUs, will also be quite interesting to make it work. It's a fun challenge, though. It's not a burden.
Yes, indeed. We are really looking forward to seeing new results after the upgrade. And if If there are no other questions, we thank Federico again and move to the next and the last talk from LHCb for today, which is Peter Spira, who is going to talk us about the Velo upgrade.
So good evening, everyone. Thank you for this opportunity. Since the previous talk very nicely summarized the general upgrade of the LHCb, I would like to focus mostly on the upgrade of the vertex locator during this long shutdown. So as you might have seen, the LHCb detector, the old detector, consists of many different subsystems. Its main purpose, it's a forward arm spectrometer with main purpose on B and C DJ physics. But in this talk, I will talk about the upgrade of the vertex locator, which is the first most tracking part in the system. So as it was mentioned, we are going to upgrade and remove the hardware trigger, so increasing the rate from 1 megahertz up to 40 megahertz readout. And this will be true for most of the LHCb system. But very specifically for the vertex locator, we are aiming to improve our resolutions as well as precisions during this upgrade, as you can see in the bottom left plots, where comparing to the previous detector, we are really reaching the maximum possibilities that can be achieved by the current technologies. If you're interested about the future upgrade that we plan for the vertex locator, you can look up the talk by Tim Evans about the upgrade that's about to happen in 10 years' time. So what are we actually changing is quite a lot in the vertex system. The biggest change is maybe increasing the number of readout channels from 170,000 to 41 million pixels, because we are switching from strip configuration to pixel configuration, while getting closer to the interaction point, to the beam, so from previous 8.2 millimeters to 5.1 millimeter. And as I said, also increasing the readout rate from 1 megahertz up to 40 megahertz, which brings a lot of complications for the general upgrade. The heart of the upgrade system is shown in this picture. This is one of the modules which we are going to install in the cavern. It's quite complex piece of equipment, but I will try to guide you through each of its individual components which are needed. To give you a slightly larger overview of the experiment, this is the upgrade. This is the plan of the upgraded vertex locator. It consists of 52 modules, which are here on each side of the proton beam, 26 modules on each side, separated from the primary vacuum by RF foil. The separation is due to different reasons, which I will talk about later, but the modules themselves are in a secondary vacuum, which is very similar to the primary vacuum. And then the readout electronics and everything else is outside, as was mentioned, in the air. So we have a complex structure to translate the signal from vacuum to the air. So the RF foil, its main purpose is to both separate the primary and secondary vacuum to avoid contamination of the beam, but also to protect the readout electronics from the beam-induced charge, since we're very close to the beam and to the interaction point. Since it's covering, as you can see in the top right picture, every module very closely with the smallest clearance less than 1 millimeter, it's obviously having an impact on the tracks and on the data taking. So following the different material budgets simulations, how the RF foil will affect the precision, but also the other parameters of the interactions, we are trying to thin it down as much as possible. And the final value is 150 microns in the thinnest region, as is shown here. The whole foil starts as a single aluminum alloy block, which is then milled down over the course of a couple months to the final element, which is then etched to the desired thickness of 150 microns, which is very precisely controlled. If anyone is interested, there is a video of the milling process, which is obviously sped up so that you don't have to spend 6 months looking at it. Following this, we already produced a number of foils with a couple of spare ones because it's an enormous piece of material which is very thin. And we also managed to install it in the LHCb cavern. And due to the COVID-19, not all of the experts could go into the cavern, so a Zoom session had to be organized with people installing it, but the experts monitoring them online and remotely helping. As I mentioned, the module, the detector, will be operated in vacuum, so we had to come up with a way how to cool down every module. And this is achieved by custom-made silicon microchannel plates, which cool up to 30 watts of power. And it's based on CO2 evaporative cooling, so that in the channels, in the cooling plate, we have a number of channels, which in the transition place trigger the boiling due to the pressure difference, the boiling of the CO2, and therefore cool down the module, the readout electronics, which is shown in the top part of this blue plate. Since I touched on the readout electronics, it's quite complex and very specific equipment. We are using Velopix ASICs, which are based on Timepix 3, so similarly sized 256 x 256 pixels, operating in data-driven readout, so without any external trigger or shuttering, only the signal that's recorded is sent out. As you can see here, 3 of these pixels are bump bonded to a sensor, and these so-called tiles are then installed on the cooling plates from both sides. So install 4 of these tiles, 2 on each side of the cooling plate. Everything is read out through wire bond connection to the readout circuitry still on the cooling plate, which is then translated through the vacuum feed-through board to the opto-power board, and then through roughly 300 meters of optical fibers to custom PCs with PCI 40 cards and FPGAs with custom firmware to further process and decode the data. Following on this, obviously the most fun part is the assembly of the individual modules. This is done in both Manchester and ICHEP. But testing and checking that everything went fine is also performed directly at CERN, and the results are cross-compared to ensure maximum efficiency. First, in the assembly, we start with bare module, so just a cooling plate with some mechanical supports, where we make sure that the cooling plate, because it's it's a very fragile part of the system, wasn't damaged. So we measure flatness first at CERN where it's made, and then at the production site to make sure nothing happened during the transport. Following this, we attach the 4 tiles, so sensors and ASICs on both sides of the cooling plate. We are using glue Sticast with catalyst 23LB deposited in this so-called star shape, which we changed from previously using catalyst 9 with a Sticast due to some humidity-related issues, which caused some minor delay in the production of the modules. As I mentioned, we have a lot of different steps that make sure that we place and build everything as we designed. So we measure glue thickness and tile flatness, as well as precise position of the tiles within 20 microns towards the LHCb coordinate system. After this, we attach front-end electronics and wire bond the ASICs to the hybrids to read out, where we again check before and after testing the strength of the wire bonds. So we pull test some of them and therefore make sure that nothing fails and everything will withstand next 10 years of operation. After this, we install low voltage and power cables. And with that, we finish the module and we are ready for the general testing. This is again done at all of the Manchester and ICHEP institutes, but also checked at CERN for consistency. First of all, we start with some simpler mechanical performance, such as taking IV scans of the tiles, which was done first at the sensor chip bonding site, then also at CERN, and then after the finished module, where the sensors are rated up to -1000 volts. Following that, we test the full readout chain, but we start with cooling down the module to designated -30 degrees. And because of different materials and components, we know that there's some bending of the material, and we need to make sure that this is within specs so it doesn't affect the online alignment that's happening. We do this by 2 capacitive sensors, which are at the end of the modules. Afterwards, we thermocycle the module 10 times so it can withstand the operation. And finally, we check what's the thermal performance of the cooling and extrapolate, because we know that with the radiation damage, the power consumption will increase, but we want to make sure that still the delta T on the sensors can be within the limits as we specified. Following all of this, we make sure that the whole readout chain works as was planned. First of all, we start to equalize the response of the ASICs to the noise floor to make sure that our data are as precise as possible. And since the readout chain is long and we have exact copy just in small scale, we also check that the data can successfully get from within the chip down to the specifically coded FPGAs. In this bottom picture, you can see the simulated ASIC data rates as we expect after installation. And as you can see, there is a higher data rate near the interaction point, so we assign more physical links to read out these chips compared to the ones that are further down the stream. We make sure we don't produce any bit errors and that our data consistency is fine. To summarize this whole upgrade, we are currently in the process of building the modules, even though the COVID-19 slightly impacted us with the closure of institutes. So we just managed to start and are in the process of recommissioning the production sites and slowly resuming building of the new modules. But at the same time, we are preparing to assemble the final vertex locator at Liverpool, so assembling the modules to the final structure, which will then be shipped to CERN, where we are already started to preparing for the commissioning of the final system. Thank you for the attention.
Thank you, Peter. Are there any questions? So first of all, congratulations for your nice presentation. Indeed, the assembly procedure is really interesting, and I would have tons of questions to you, but I would just quickly ask you whether you have an idea of the yield you're expecting for the assembled modules.
We did quite extensive R&D with some testing modules, which I think we built 6 fully functional modules. So we are expecting to have almost 100% of newly produced modules to be fully functional that could be used in the final system.
Oh, okay, thank you. So very high efficiency. Is there anyone who wants to ask something to Peter? Well, doesn't seem so. So maybe we can close your presentation. Thanks you again. And let's move to our last presentation for today. That's Felix Müller, who is going to talk us about the pixel vertex detector for Bell 2.
Yeah, thank you for the opportunity to show you the first 1.5 years of experience with the pixel vertex detector at Bell. Since I have the first talk in this session about SuperCAC-B or Bell. I will give a very brief reminder of what the experiment is about. So SuperCAC-B is an asymmetric electron-positron collider at the center of mass energy of the epsilon-4s resonance, with the goal integrated luminosity of 50 inverse autobahn. And to reach this, we have to increase the luminosity largely compared to the predecessor. And this is mainly done by reducing the vertical beam size to a so-called nanobeam structure and increasing the beam currents. And of course, you also have to upgrade your detector accordingly. Here I will only focus on the inner pixel detector, which is a 2-layer detector at radii of 14 and 22 millimeter. Couple of highlights from the first runs was basically in March 2019 that we had our first physics data. And also in June this year, we achieved the world record instantaneous luminosity for a colliding beam accelerator. As the technology for the pixel detector, we choose the depth-fed technology for the very first time in a collider experiment. As a reminder, what is the depth-fed technology? A depth-fed pixel basically consists of a field effect transistor, and you add an additional N implant underneath your gate. This implant is called the internal gate, which is a potential minimum for electrons. So when you create then electrons inside the pixel, they are accumulated in this internal gate, and with capacitive coupling, it modulates the transistor current. To basically get the next hit, you have first to clear the electrons from the internal gate, and for this you have a clear contact which then punches through to this internal gate to remove the electrons. The advantage of this technology is that you have detection and internal amplification in one go, which gives you a very good signal to noise ratio and allows you to build low power consumption detectors and very thin detectors, which is very important here. Here you can see the module design that we are using. We have 250 times 768 pixels per module. The pixel pitch varies a bit in Z and also from the inner and outer layer, but in principle it's about 50 times 55 micrometers squared. And the thickness of the sensor was optimized to have the best performance in the forward direction at around 45-degree angle. Basically, you have to wait off multiple scattering with enough charge sharing and signal strength. And our optimal point for the vertex resolution was 75 micrometer thickness. You can see here in the bottom right, a cross-section of the module where you see that the matrix here is really thinned down to 75 micrometer. The border of the module is kept thicker so that it's mechanically self-supporting. But in total, still you only have about 0.21% radiation length per layer in the physical acceptance region. The readout concept is a simple rolling shutter mode, but we don't read out single rows, but so-called gates, which are just a combination of 4 adjacent rows. And the rolling shutter leads to a full integration time of 20 microseconds, which is twice the revolution time of the accelerator. The advantage, as I said before, is that you only need to activate roads which are actively read out. So with this, you can really reduce the power consumption of your matrix. We had to develop 3 custom-made ASICs for the operation of the module. You see here at the side of the matrix, there are 6 so-called switchers. And as the name suggests, it's responsible for switching the voltage of the gate and the clear signals very fast in the order of 20 nanoseconds. Then we have developed this DCD. We have 4 of these DCDs on every module. It digitizes the current signal from the transistors. Each chip has 256 input channels, and each channel has an 8-bit pipeline ADC. The sampled data is then processed by the data handling processors. Also 4 of these are on each module, which then handles everything else like pedestal correction, zero suppression, and timing and triggering. And also finally, doing the data transmission with 1.6 gigabits per DHP. Of course, all three ASICs have been tested on the radiation hardness to sustain the background, which is expected at SuperCAC-B. Here you can see a picture of the installed detector. On the top right, you see that we did not manage to install the full 2-layer detector, but only the inner layer and 2 of the outer segments. The main problem is you see that we have here actually 2 modules always glued together in the center, and this gluing process caused quite some errors in the production, which led to us that we only managed to install this half the detector basically. And here you can see also then the remaining vertex detector, which is a silicon strip detector, 4 layers being placed around the inner pixel detector. Yeah, also only half a shell before it gets close to volume. So performance-wise, the modules are very good. We have here on the top right, you see the noise performance of one of the modules. We have a noise typically below 1 ADU, which is of the order of 200 electrons, also very homogeneously distributed across the matrix. And our average charge signal is of the order of 40, which gives you a signal to noise ratio of between 30 and 50, also rather homogeneously across the whole matrix. So what can you then measure with something like this? What we did here is we reconstructed the beam profile from the vertex information. As a reminder, the beam profile at SuperCAC-B is very elliptical. It's very thin in Y, so thin that we can neglect it here as it's below our resolution. And in X, we have 15 to 10 micrometers. In the top right, we were able to reconstruct the beam profile by using phi dependence of the track impact parameter resolution, and the results are in a very good agreement with the expectations. In the bottom right plot, it uses a slightly different approach using a full covariance matrix of the track data, but the PXC here helps to reduce the amount of data that is needed, so you can really reconstruct the beam size on a run-by-run basis, or even you could check for changes within runs. And also here, the data reconstruction in black is in good agreement with the expectation from the accelerator optics parameters in red. And physics-wise, maybe as a highlight, you will see that in a talk by Julia Casarosa in 2 days. You see here the lifetime of the charm, where a negative lifetime is, of course, non-physical and only comes from your detector resolution. And you see that with the current PXD and inside the Bell 2 detector, we achieved a factor of 2 improvement compared to previous B factories. In terms of efficiency, you see here a map of the efficiency of the inner layer, and you directly see that there is one large chunk missing. That is one module which was already badly graded when we installed it, and it failed pretty early on. Unfortunately, we didn't have a replacement that we could use. But of course, it is exactly in the point where we have a second layer installed, which helps to reduce the degradation of the performance, since you can still use the second layer for vertexing. But you see other features as well. On the one hand, you see these phi gaps. This comes from the fact that we installed the detector as 2 half shells around the beam pipe, and we had some difficulties there as well, so that they are not fully in the place that we wanted them, so that you still have these gaps in between this. Then you see these gaps here. These are the glue gaps between 2 modules. They are just curved because it's a projection on tangents lambda. You see on the right-hand side, if you look in through Z of the modules, he is actually then the transition between two of these modules, where you nicely can see this glue gap of about 0.8 millimeter. In the good regions, we have a very good hit resolution of hit efficiency, sorry, of about 99%. But what you also see are these red stripes, and these are actually dead gates. So actually 4 rows that are not working and degrade the overall hit efficiency by 2%. And why do we have so many? And the cause is that we had so-called what we call beam loss events. So what happened is that the beam was lost very close to the detector, and this caused large radiation bursts hitting the detector, even heating up the final focusing magnet so much that it quenched. And these radiation bursts damaged our detector. You can see that here, for example, the efficiency map before one of these beam losses and here after. And you directly see that there are many more of these dead gates appearing. I said before that we, in principle, have tested the ASICs on their radiation tolerance, and that is true. But of course, we didn't test them on these radiation bursts, only on a longer time scale. And this is something that we're currently studying at a test beam campaign in Mainz here in Germany, where we try to identify regions in especially the switcher ASIC, which is sensitive to radiation bursts. But of course, we cannot exchange the PXDs that easily, and especially not the ASICs. So we kind of need to work on improving our protection scheme. And there we are working on 2 fronts. On the one hand side, we have the accelerator, which try to minimize the occurrence of these events and also shorten the time between the detection of these events and the actual abort of the beam. On the PXD side itself, we are also trying to improve our reaction time basically by, at the moment, it takes about 100 milliseconds from a beam abort signal until the modules are actually shut down. And we want to reduce that to about 100 microseconds, mainly by modifying our power supplies because the time constants at the moment are just too large, and we will do some active shutdown procedure here. And with this, I come to my summary and outlook. So we had the very first experience with this new pixel technology, DepFET, in a full-scale detector at an accelerator. The overall performance was very good and stable, except of that we had these beam loss events which damaged our detector, and also in the accelerator and the PXD group needs to work on minimizing the probability and also the impact of these uncontrolled beam losses. And as an outlook, I showed you that we only installed half of the detector due to the problems with the gluing process, and we will install the full detector in 2022, since we need the second layer to to reach our physics goal when we have the full luminosity. Thank you.
Thank you, Felix. So, any questions to Felix?
Maybe I would have a question if I can.
Sure.
So I would like to ask you, of course, these beam losses are the big, very dangerous thing. Is there some active or passive protection present in your sensors or the electronics that could somehow protect the modules before this?
For these beam losses, there are some ideas to add some additional shielding, but the best solution would be to basically that the modules are off. And this is what we try to do here, that as soon as we detect some higher radiation, we have special diamond sensors for that installed that actually detect this appearance. And if they react, we want to shut down the modules as fast as possible, and then we cannot damage the switch anymore.
Okay, and do you see some chance, for example, in the future for some upgrade, how to test your modules against these things? For example, in our campaign, for example, ITK strip, we are using this high-rat-mat facility at CERN, where you can somehow check against. Of course, these are protons, and you don't have protons probably, but I don't know if there is some way.
We use this mummy test beam at the moment to basically really scan the switcher ASICs and see if we can reproduce the damage. Yeah, but this is something that we are currently looking into, what kind of irradiation sites we have to further test this more roughly.
Okay, and the last question from me, would you plan, or do you plan to change these damaged modules in the future?
So what I said that we exchanged the PXD and we will actually use complete new modules for that. So we will not reuse the one that are installed, but complete new modules.
Okay, thanks.
Okay, so thank you, Felix, for the nice presentation, and thank you to all the speakers. So we close here today's session, and we see each other tomorrow.
Yes, thank you very much. Thank you for sharing, and thank you for joining this very long session. I think that now we can actually stop recording. There is, of course, a very wide or rich program for tomorrow. So from 8 a.m. Prague time, there will be a replay of this session. Of course, it's necessary to go there if you were here. Then we have a poster sessions for track 12 starting at 1:30 p.m. Prague time. And after these poster sessions, there will be like a half an hour break, and we will start with the second parallel sessions that will go again something like 5 hours long, up to something like 8:30 p.m. Prague time. So yeah, tomorrow we have a wide rich program. By the way, now we will probably stop recording, but of course, as I mentioned at the beginning, we can easily continue in the discussion. So if there would be some topic that we would like to discuss, or even very non-formal things, whatever can be discussed, so you can stay logged into this Zoom room. It will be open and we can discuss whatever you would like to discuss. So yeah, thanks again for joining, and see you tomorrow.
Thank you all. See you tomorrow.
Thank you. Goodbye. See you.
Bye-bye.
Okay, Tadeusz, are you there?
Yes, I will just post the links and set up the screen of the end session.
Okay. I will just ask you if the recording was okay for you, and you will have a good backup or good record.
Yes, for me, yes. Except that I forgot to stop for the first coffee break, but it's fine.
I think that's fine. Yeah. Unfortunately, my Zoom was unexpectedly closed, and so I think that the record on my side will be broken completely.
Yeah. So here it should be fine.
Okay. Perfect. Thanks. So Michal, how it was going in track 13?
Well, we had 55 people, 19 talks, and it was quite packed, but it's a successful, no problems with connection. We took a recording with everything. But the problem with these online conferences is that there is not much social interaction, so there were not many questions.
Yeah. We had a similar problem, I would say. And people are more and more tired in the time. So yeah, it's worse and worse in the time, I would say.
I just hope this doesn't become the new standard of conferences, this online thing.
No, I don't. I hope that not.
Yeah. So I guess this is for the discussion after session.
Yeah, very probably. What about your Mattermost chat? Was it used?
Sometimes, yes, people were sending links, asking a few questions, but I think for the purpose of this, it would be of the same use if we use this online chat.
Yeah.
But in here, at least it's persistent. So if somebody logs in tomorrow, they can still see the questions.
Yeah. Yes, definitely. Okay.
I guess that's it.
Probably yes. By the way, Tadeusz, what is the situation in the center? How it was working? Do you have some messages from the other ZTAs? Was it going smoothly? Oh. He's probably no more.
Yes.
Okay. Yeah. Everybody too tired.
Okay, so I guess let's get to sleep and let's wake up tomorrow and prepare the slides for the.
No, sorry. I just couldn't find the button.
Yeah. Okay. So I'm just curious. What is the situation there?
One session 6 is still have 2 talks to finish, I guess, or 1.
Sorry, what does it mean?
Sorry, can you hear me? Session 6, 1 or 2 talks finish, but otherwise they are fine.
Okay. So everything was going smoothly.
Yes.
Okay, perfect. So tomorrow for track 12, you will be the ZTA again?
Yes, and I had one question for the replay. Should I arrive also? It's no problem for me. So, but
I probably if there is somebody from the organizers, please ask them. I will be very probably present, and I will regularly check the Metromos channel. I don't know how is it with the stream. I think so please ask them if you should be there, or if somebody should be checking the stream or the YouTube stream if it is running smoothly. So yeah, I would recommend to ask them. I really don't know.
Okay.
So for me, I will be yes.
And the conversion will be also done afterwards, probably in the morning, right? By someone.
Yeah, I don't know how is it working for you. Probably you need to double click this, or you will just let it go, or I don't know. What are your instructions? I think
I didn't want to touch anything to not break the conversion of the video because we will handle by
and it is converting automatically.
Yeah, it should be so.
Okay.
That's something like that.
Okay, better ask because we don't have backup, so better ask what should be done.
Okay. So I'm disconnecting now.
Okay, yes. I think that we can close this.
Yep.
Okay, so see you tomorrow. Bye.
Bye.